Imagine a place where light itself is held captive, bending around cosmic curves so extreme that reality itself seems to twist into impossible shapes. This isn't science fiction, it's the enigmatic world of gravitational labyrinths, where the very laws of physics create mazes that challenge our deepest understanding of the universe. For centuries, we've looked up at the night sky and wondered about the nature of light and gravity, but only in recent decades have we begun to grasp how these fundamental forces interact in ways that defy our everyday experience. What if I told you that there are regions in space where light becomes trapped in endless loops, where time itself may twist back on itself, and where the fabric of reality forms puzzles that even our brightest minds struggle to solve? Today, we're embarking on an extraordinary journey into these impossible worlds, exploring the phenomenon of trapped light and the mind-bending physics behind gravitational labyrinths. We'll travel from the theoretical foundations laid by Einstein over a century ago to the cutting-edge discoveries that are reshaping our cosmic perspective right now. Along the way, we'll discover why this topic captivates astronomers and physicists alike, not just as mathematical curiosities, but as potential keys to unlocking the universe's greatest secrets. From black holes that swallow light whole to theoretical wormholes that might connect distant regions of spacetime, we're about to explore frontiers where our conventional understanding of physics reaches its limits. This exploration matters because it touches on something fundamental to human nature, our relentless curiosity about the cosmos and our place within it. Gravitational labyrinths represent one of the most fascinating puzzles in modern astrophysics, challenging us to rethink everything from the nature of reality itself to the possibility of realms beyond our current perception. As we dive into these mysteries together, prepare to have your perspective shifted, your imagination ignited, and your sense of wonder expanded. We're about to unravel the intricate dance between light, gravity, and space-time, and in doing so, we might just catch a glimpse of realities that until now have existed only in the realm of theory and imagination. So settle in, open your mind, and join me as we begin this adventure into one of space's most intriguing and mysterious frontiers. To understand how light can become trapped in cosmic labyrinths, we first need to grasp the fundamental nature of light itself and its relationship with gravity. Light behaves in two seemingly contradictory ways as both a particle and a wave. These tiny packets of energy, called photons, travel at the universe's ultimate speed limit, yet they're not immune to gravity's influence. For centuries, scientists believed light traveled in perfectly straight lines, unaffected by gravitational forces. It was Albert Einstein who revolutionized this understanding with his theory of general relativity, proposing that what we perceive as gravity isn't actually a force pulling objects together, but rather the curvature of spacetime itself caused by mass and energy. Imagine spacetime as a flexible rubber sheet. When you place a heavy object like a bowling ball on this sheet, it creates a depression. Now, if you roll a marble nearby, it will naturally curve around this depression rather than continuing in a straight line. Einstein realized that light behaves much like that marble. It follows the curvature of spacetime. The more massive the object, the deeper the curvature, and the more dramatic the bending of light's path. This was a radical departure from Newton's view of gravity, where light particles might be affected by gravity, but would still primarily move in straight lines unless directly pulled. The true brilliance of Einstein's theory was put to the test during the total solar eclipse of May 29, 1919. British astronomer Arthur Eddington led an expedition to measure the apparent positions of stars near the Sun's obscured disk. According to general relativity, the Sun's mass should warp the spacetime around it, causing starlight to bend and making those stars appear slightly out of position. The measurements matched Einstein's predictions almost exactly, providing the first compelling evidence that mass could indeed curve the path of light. This confirmation catapulted Einstein to worldwide fame and established general relativity as a cornerstone of modern physics. What makes this bending of light so fascinating is that it doesn't require exotic conditions or extreme environment. It happens throughout our universe every day. This phenomenon, now known as gravitational lensing, occurs whenever light passes near any massive object, from planets and stars to entire galaxies. Sometimes the effect is subtle, causing tiny shifts in apparent positions. Other times, it can create dramatic multiple images of distant quasars or beautiful Einstein rings, where light is distorted into perfect circles around massive galaxy clusters. These everyday demonstrations of light bending show us that the seeds of more extreme light-trapping phenomena are woven into the very fabric of how our universe operates. The key insight here is that gravity doesn't attract light in the traditional sense. It alters the geometry of the path that light must follow. Photons always take the most direct route through spacetime, but when spacetime itself is curved, that most direct route might not be a straight line to outside observers. This understanding forms the essential foundation for everything we'll explore next about gravitational labyrinths. Once we appreciate how ordinary matter can bend light under normal circumstances, we can begin to imagine what happens under extraordinary conditions where spacetime becomes so severely warped that light can't escape at all. Now that we understand how gravity bends light under normal circumstances, let's explore what happens when this curvature becomes so extreme that it transforms spacetime itself into an inescapable maze. These are gravitational labyrinths, regions where the fabric of reality twists and folds into such complex patterns that anything entering, including light, may never find its way out. Picture not just a gentle curve in spacetime, but an entire intricate network of tunnels, dead ends, and loops where the normal rules of navigation break down completely. These cosmic mazes form under the most extreme gravitational conditions imaginable, typically in the vicinity of objects so dense that their gravity overwhelms all other forces in the universe. The most common natural laboratories for these phenomena are black holes, especially supermassive ones at the centers of galaxies. Here, matter is compressed to such incredible densities that space-time curvature becomes infinite at the singularity, creating gravitational fields so powerful that not even light can achieve escape velocity. But gravitational labyrinths aren't limited to black holes. Theoretical constructs like wormholes, if they exist, could create even more complex maze-like structures. In a wormhole scenario, spacetime might fold back on itself, creating shortcuts through the universe that could feature multiple pathways, chambers, and loops where light might circulate endlessly without ever reaching an exit. To visualize how these labyrinths operate, imagine our earlier rubber sheet analogy, but now with not just one depression but multiple overlapping warps, twists, and folds. A marble representing light might roll into a region where the surface curves so severely that it enters an eternal orbit, or it might encounter a tunnel that connects to another part of the sheet entirely. In some configurations, the paths might shift and change dynamically, creating a maze that constantly rearranges itself. This isn't merely theoretical. Mathematicians have solved Einstein's equations to show that such complex spacetime structures are possible within the framework of general relativity, given specific conditions and matter distributions. What makes gravitational labyrinths particularly fascinating is that they're not necessarily science fiction or mathematical abstractions. They could be real features of our cosmos. The detection of gravitational waves from merging black holes and neutron stars has provided indirect evidence that extreme spacetime curvature behaves largely as predicted by Einstein's equations. Some physicists theorize that certain types of dark matter formations or quantum gravitational effects might create less extreme but equally fascinating gravitational labyrinths throughout the universe. These might not trap light permanently, but could create complex patterns of deflection and delay that reveal the hidden structure of spacetime itself. The implications of these cosmic mazes extend far beyond theoretical interest. If we can understand how gravitational labyrinths form and operate, we might unlock secrets about the nature of singularities, those points of infinite density where our current physical theories break down. They could provide clues about the mysterious dark matter that makes up most of the universe's mass but remains invisible to our telescopes. Perhaps most intriguingly, studying these spacetime structures might help bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that have resisted unification for nearly a century. Each trapped photon or circling particle in these labyrinths carries information about the fundamental nature of reality, waiting for us to learn how to decode it. Building on our understanding of gravitational labyrinths, let's focus on one of the most fascinating and well-studied examples, the photon sphere. This is a precise region around a black hole where gravity becomes so intense that it forces light itself into a perfect circular orbit. Picture this, a shimmering ring of photons circling the black hole at the speed of light, perpetually suspended between escape and capture. These aren't just theoretical curiosities, they represent a delicate and unstable balance point in spacetime, a place where light is neither free to fly away into the cosmos nor doomed to fall inward past the event horizon. The concept of photon spheres emerged from solutions to Einstein's field equations. When Carl Schwarzschild first solved these equations for a non-rotating black hole, he discovered that at exactly 1.5 times the Schwarzschild radius, the distance defining the event horizon, something remarkable happens. Light can orbit the black hole in a circular path. Later, physicists like Brandon Carter and Roger Penrose expanded this to rotating black holes described by the Kerr metric, where the photon sphere becomes more complex, shaped by the black hole's spin into oblate regions that can even split into multiple orbital paths. These discoveries showed that under the right conditions, gravity can sculpt light itself into captive rings. The stability of these orbits is incredibly tenuous, like balancing a marble on the edge of a curved knife. Light in a photon sphere exists in what physicists call an unstable equilibrium. The smallest disturbance, a passing gravitational wave, a slight interaction with dust or gas, or even the subtle influence of other photons, can nudge it off its precarious path. If perturbed outward, the photon might gain enough energy to escape the black hole's grip, flying off into space. If nudged inward, it crosses the event horizon, disappearing from our observable universe forever. This fragility makes photon spheres not just traps, but also natural amplifiers of electromagnetic activity around black holes. Our ability to study these phenomena took a giant leap forward with the Event Horizon Telescope collaboration. When they released the first image of a black hole's shadow in 2019, showing the supermassive black hole at the center of Galaxy M87, we weren't just looking at the event horizon. That dark central shadow was surrounded by a bright ring of light, emission from hot, accelerated matter, but also shaped by the lensing effects of the photon sphere itself. The sharpness of that ring provided indirect but compelling evidence for the existence of these light-trapping regions, matching predictions from general relativity with stunning accuracy. Theoretical work by physicists like Kip Thorne has been crucial in interpreting what we see and what we might see near photon spheres. Thorne's contributions, both in academic research and in popular science communication, have highlighted how these regions serve as natural laboratories for testing the limits of general relativity. In his work as a scientific consultant on the film Interstellar, Thorne helped visualize what an accretion disk might look like when lensed by a rapidly spinning black hole's photon sphere, creating the multiple, warped images that became iconic in the movie. This blend of rigorous science and public engagement has made photon spheres a gateway for understanding how extreme gravity shapes our view of the universe. Beyond their role as cosmic curiosities, photon spheres act as boundaries between knowable and unknowable realms of spacetime. They mark the last point from which light can still escape, making them the ultimate observational frontier. Anything inside the photon sphere that isn't already on a precise orbital path is almost certainly destined for the event horizon. This makes them critical for understanding how black holes interact with their environments, how they accrete matter, emit jets, and influence the growth of galaxies. By studying the dynamics of photon spheres, we gain insights into the behavior of matter and energy under conditions so extreme they defy earthly intuition. What makes photon spheres particularly valuable to astrophysicists is that they offer a tangible, observable manifestation of trapped light, a concept that might otherwise seem purely abstract. Unlike the mathematical singularity at a black hole's center, which remains hidden behind the event horizon, photon spheres theoretically could be probed and studied if we could get close enough. They represent a threshold where the familiar rules of light and motion give way to the bizarre predictions of general relativity, providing a crucial stepping stone toward understanding even more exotic gravitational phenomena. To truly appreciate how we arrived at the mind-bending concept of light being trapped by gravity, we need to rewind the clock and walk through the fascinating evolution of scientific thought on this matter. Our story begins not with Einstein, but with Sir Isaac Newton in the 17th century. Newton, who so brilliantly unraveled the mathematics of gravity with his law of universal gravitation, also pondered the nature of light. He proposed what was known as the corpuscular theory, the idea that light was composed of a stream of tiny, discrete particles. If light was made of particles, he reasoned, then surely these particles should have mass and therefore be subject to the pull of gravity, just like an apple falling from a tree. This was a logical starting point, but it was incomplete. Newton's theory could predict that gravity would affect light, but it struggled to explain precisely how or to what degree, and it certainly couldn't account for light's wave-like behaviors that were beginning to be observed, such as interference and diffraction. For over 2 centuries, this was the prevailing view. Light and gravity were connected, but the relationship was murky and not fully understood. The scientific world needed a revolution, and it arrived in the form of a young patent clerk named Albert Einstein. In 1905, his Annus Mirabilis, or Miracle Year, Einstein published his theory of special relativity, which forever intertwined space and time into a single continuum, spacetime. But it was his later work, culminating in his theory of general relativity published in 1915, that truly shattered our classical understanding. Einstein proposed a radical new idea. Gravity isn't a mysterious force acting across a distance, as Newton thought. Instead, it is the curvature of this spacetime continuum itself caused by the presence of mass and energy. A massive object like the Sun doesn't pull on the Earth. It simply warps the spacetime around it, and the Earth follows the most direct path through that curved geometry, a path we perceive as an orbit. This geometric view of gravity had profound and testable implications for light. If spacetime is curved, then light, which always follows the shortest path through spacetime, a geodesic, must have its path bent as well. Einstein's equations predicted two key phenomena that Newton's theory could not: gravitational redshift and the bending of starlight. Gravitational redshift describes how light loses energy and its wavelength stretches as it climbs out of a gravitational well like that of a star. The bending of starlight was an even more dramatic prediction. Einstein calculated that light from a distant star passing near the limb of the sun would be deflected by a precise, measurable angle, an effect exactly twice what would be predicted by Newton's corpuscular theory alone. The validation of this prediction is one of the most celebrated stories in science. During the total solar eclipse of May 29, 1919, expeditions led by Sir Arthur Eddington to Sobral, Brazil, and Principe Island off the coast of Africa measured the apparent positions of stars near the sun's darkened disk. Their photographs confirmed that the starlight had indeed been bent, precisely matching the predictions of general relativity. This catapulted Einstein to international fame and cemented his theory as the new description of gravity. But the theoretical breakthroughs didn't stop there. Almost immediately after Einstein published his field equations, the German physicist Karl Schwarzschild found a solution to them describing the gravitational field around a spherical, non-rotating mass. Tragically, he did this while serving on the Russian front during World War I, and he died shortly after from an illness. His solution, now known as the Schwarzschild metric, was the first to mathematically describe the concept we now call a black hole. It contained a boundary, the event horizon, and crucially, it defined a specific distance from the center of the mass where something extraordinary could happen: a photon sphere, a place where light could orbit in a perfect circle. For the first time, the equations of physics had not just suggested that light could be bent, but had explicitly defined a region of space where it could be permanently trapped. This was the mathematical birth of the gravitational labyrinth. Later, physicists like Roy Kerr would find solutions for rotating black holes, adding even more complexity and potential pathways for light to become ensnared. This historical progression shows that our modern ideas about trapped light aren't sudden inventions. They are the natural, if astonishing, culmination of a chain of reasoning that began with Newton and was forged into its modern form by Einstein and the brilliant minds who built upon his work. Each step built directly on the last, deepening our understanding and revealing a universe far more strange and wonderful than anyone had previously imagined. Now, if gravitational labyrinths are the cosmic mazes, then black holes are their most perfect and terrifying architects. These celestial objects represent the ultimate expression of gravity's power, where space-time is warped so severely that it creates a one-way street into oblivion. At the heart of every black hole lies a singularity, a point of infinite density where the known laws of physics simply cease to function. This isn't just a very dense object. It's a place where our current understanding of reality hits a wall, a mathematical breakdown that hints at a deeper theory waiting to be discovered. Surrounding this enigmatic center is the event horizon, the famous point of no return. Think of it not as a physical surface but as an information firewall. Once any particle or even a photon of light crosses this boundary, it can never communicate with the outside universe again. Its fate is sealed, irretrievably lost to the singularity. But the story of light near a black hole is far richer than just a simple plunge into darkness. Outside the event horizon, the gravitational landscape becomes a complex and dynamic labyrinth. For a non-rotating black hole, the Schwarzschild solution describes a precise sphere, the photon sphere we discussed earlier, where light can orbit in perfect, if unstable, circles. However, most black holes in the universe are likely spinning, described by the more complex Kerr metric. A rotating black hole drags the very fabric of spacetime around with it, an effect known as frame dragging. This rotation creates a region outside the event horizon called the Ergosphere, a squashed, oblate shape where nothing can remain stationary. It's a cosmic whirlpool where spacetime itself is set into a furious spin. Within the ergosphere, the paths available to light and matter become even more bizarre and chaotic, a true gravitational maze where trajectories are twisted into complex spirals and loops before their final descent. The incredible complexity of this environment was brought into stunning focus with the Event Horizon Telescope's landmark image of the supermassive black hole at the heart of Galaxy M87. That now iconic picture of a dark shadow encircled by a fiery ring wasn't a direct photograph of the black hole itself, but a masterpiece of inference shaped by the black hole's gravitational labyrinth. The bright ring is primarily light from the superheated accretion disk, but its precise appearance is dramatically molded by the photon sphere. The light we see is bent and lensed by the extreme gravity, with photons making multiple orbits before either escaping to our telescopes or vanishing forever. The dark central shadow is actually larger than the event horizon itself, a gravitational magnifying effect that reveals the point where light paths plunge into the abyss. This image wasn't just a confirmation of black holes, it was a detailed map of the gateway to a gravitational labyrinth. Theoretical work has been crucial in interpreting what we see. Physicist Roger Penrose won a Nobel Prize in part for his work showing how the energy of a rotating black hole could, in theory, be extracted, a process now known as the Penrose process. If an object enters the ergosphere and splits in two, with one part falling into the black hole, the other part could be flung out with more energy than it came in with, essentially stealing energy from the black hole's rotation. This isn't just a theoretical curiosity. It might explain the incredible power of jets shooting from active galactic nuclei, where magnetic fields and plasma interact with the black hole's spin in this chaotic region. Black holes are not just simple drains on the universe, they are engines of immense power, and their gravitational labyrinths are the complex machinery that makes it all possible. These cosmic objects truly are the ultimate laboratories for extreme physics. They push matter and energy to their absolute limits, creating environments where quantum mechanics and general relativity are forced to collide. The chaotic dynamics within these gravitational labyrinths, the way matter is compressed, heated, and accelerated, generate conditions we could never hope to replicate on Earth. By studying how light behaves as it navigates this final maze, teetering on the edge of the event horizon, we are probing the very boundaries of human knowledge. Every photon that manages to escape and reach our detectors carries with it a story from the edge of the unknown, a tale woven in the intense curvature of spacetime that defines our universe's most perfect traps. But if black holes represent nature's ready-made gravitational traps, then wormholes offer perhaps the most tantalizing possibility of all, theoretical tunnels through spacetime itself that could act as the ultimate cosmic shortcut. Imagine the universe not as a vast, flat expanse, but as a folded piece of paper where two distant points are brought nearly together. A wormhole would be a bridge connecting those points, a hypothetical passage that could, in principle, allow for travel across immense cosmic distances in a fraction of the time it would take light to make the journey through normal space. These aren't just simple tunnels, though. If they exist, their interiors could form unbelievably complex gravitational labyrinths where the very concepts of direction and time become tangled. The modern scientific exploration of wormholes began in earnest with the work of physicists Albert Einstein and Nathan Rosen. In 1935, they discovered that the equations of general relativity allowed for a structure that connected two different regions of spacetime, a bridge, as they called it, which we now know as an Einstein-Rosen bridge. However, these early versions were essentially mathematical curiosities. They were unstable, would collapse instantly if any matter tried to pass through, and were intrinsically linked to the singularities of black holes. The real breakthrough came decades later when physicists like Kip Thorne and his student Mike Morris re-examined the idea. They asked a deceptively simple question rooted in science fiction: could a wormhole ever be traversable by humans? Their answer, published in 1988, was a cautious maybe, but it came with an enormous catch. They formulated what is now known as the Morris-Thorne metric, a mathematical description of a stable, traversable wormhole. This model revealed the incredible engineering required to prop such a tunnel open. The entrance, or mouth, of the wormhole would need to be threaded with something known as exotic matter. This isn't antimatter or dark matter. It's a hypothetical substance that possesses negative energy density and negative pressure. In simple terms, unlike normal matter which gravitationally attracts, exotic matter would gravitationally repel. It would act as a kind of anti-gravity force, counteracting the immense pressure that would otherwise cause the wormhole's throat to pinch shut instantly. The problem is, while quantum mechanics allows for the existence of tiny amounts of negative energy in certain circumstances, like in the Casimir effect between two closely spaced plates, the quantities needed to stabilize a wormhole large enough for travel are astronomical and far beyond any technology we can conceive. Within the throat of a theoretically stable wormhole, light would behave in utterly bizarre ways, potentially creating the most perfect gravitational labyrinth imaginable. Photons could loop around and around the tunnel's curvature in closed orbits, never exiting either end. If you were to shine a flashlight into one mouth, you might see the light emerge from the other mouth, but you might also see it curve back and come right back at you, or even split into multiple images tracing different paths through the tunnel's geometry. This could create visual feedback loops and infinite regresses of images, a hall of mirrors crafted not from glass but from the warped fabric of spacetime itself. The potential for light to become permanently trapped in these complex pathways is immense, making a stable wormhole a prison from which not even light could easily escape. Perhaps the most mind-bending implication of certain wormhole models is their connection to time travel and paradox. If one mouth of the wormhole were moved at relativistic speeds or placed in a strong gravitational field, time would pass at different rates at each end, as predicted by general relativity. This could effectively turn the wormhole into a time machine, creating what physicists call a closed time-like curve. An object or a beam of light entering one end could exit the other end at a moment in time before it even entered. This immediately raises famous paradoxes like the grandfather paradox, where you could potentially go back and prevent your own existence. The late Stephen Hawking proposed the chronology protection conjecture, which suggests the laws of physics might actually prevent such time travel from occurring, perhaps through a buildup of quantum energy that would destroy the wormhole the moment it became a time machine. This highlights the fierce debate between mathematical possibility and physical plausibility. The cultural impact of wormholes, heavily influenced by Kip Thorne's work as a scientific consultant on the film Interstellar, cannot be overstated. Thorne insisted that the movie's depiction of the wormhole, Gargantua, be based on real scientific equations, leading to visual effects that accurately portrayed the gravitational lensing and the warped view of a distant galaxy seen through its tunnel. This collaboration between science and cinema did more than just create a stunning visual. It popularized a complex astrophysical concept and inspired a new generation to ask questions about the nature of our universe. It perfectly illustrates how these speculative ideas, while far from proven, serve a vital role. They stretch our imagination, challenge our theories to their breaking points, and in doing so, often guide us toward deeper truths about the cosmos, pushing us to wonder how we might one day detect such fantastical structures hidden within the fabric of reality. While the theoretical constructs of black holes and wormholes present mind-bending possibilities, we don't have to rely solely on theory to witness gravity's light-bending power. We can actually observe it happening across the cosmos through a phenomenon called gravitational lensing. This is where the gravity of a massive object like a galaxy or a black hole acts as a cosmic lens, warping the spacetime around it and deflecting the path of light coming from objects far behind it. It's not a trap that holds light forever, but it's a real-world, observable example of a gravitational labyrinth in action, subtly guiding light along curved and twisted paths. The effects can range from a simple, slight magnifying effect to the most dramatic and beautiful optical illusions in the universe. The most striking example of this is the Einstein ring, a perfect or near-perfect circle of light that forms when a distant galaxy, a massive foreground galaxy, and our telescope are all in perfect alignment. The foreground galaxy's gravitational field bends the light from the background source, wrapping it around itself to form a luminous halo. It's a direct validation of Einstein's prediction and a breathtaking demonstration of spacetime's flexibility. Sometimes the alignment isn't perfect, and instead of a complete ring, we see multiple images of the same distant object arrayed around the central lens like points on a clock face. These cosmic mirages are more than just curiosities. They are powerful tools that astronomers now use to do things once thought impossible. One of the most critical applications of gravitational lensing is in the hunt for dark matter. We cannot see dark matter directly as it doesn't emit, absorb, or reflect light, but we can most definitely detect its gravitational influence. By studying how galaxy clusters' enormous collections of hundreds or even thousands of galaxies act as gravitational lenses, we can map their total mass. This includes the mass of the visible stars and gas, but also the immense, invisible halo of dark matter that surrounds them. The light from background galaxies is distorted in a specific way, an effect known as weak lensing, which allows scientists to create detailed maps of the dark matter's distribution. It's like deducing the shape of an invisible object by watching how it distorts the view of something behind it. The utility of this natural telescope doesn't stop there. Gravitational lensing also acts as a natural magnifying glass, amplifying the light of incredibly distant and faint objects that would otherwise be far beyond the reach of our most powerful telescopes. This allows us to peer back into the early universe, studying the formation of the first galaxies. Furthermore, on a much smaller scale, a technique called microlensing has become a surprisingly effective method for discovering exoplanets. If a star with planets passes in front of a more distant background star, the gravity of the foreground star and its planets can briefly magnify the light of the background star. By carefully analyzing the distinctive brightening pattern in the light curve, astronomers can not only detect the star's planets but even infer their masses and orbits. We have the Hubble Space Telescope to thank for some of the most iconic and convincing evidence of this phenomenon. Images from Hubble, like the famous Hubble Deep Field and later the Frontier Fields project, are littered with stretched, smeared, and curved arcs of light, all galaxies whose light has been dramatically warped by the gravitational fields of immense galaxy clusters lying between them and us. These observations do more than just produce pretty pictures. They provide rigorous, quantitative tests of general relativity on cosmic scales and offer an indispensable window into the universe's large-scale structure. Every distorted galaxy we see is a testament to the fact that the gravitational labyrinths we theorize about have real, observable cousins in nature. proving that space-time curvature is not just a mathematical abstraction but a physical force that shapes our view of the cosmos. So if wormholes and warp drives are the cosmic architecture, then exotic matter is the utterly strange and essential building material required to bring these gravitational labyrinths to life. This isn't the dark matter we hear so much about, nor is it antimatter, which still has positive energy. Exotic matter, as defined by general relativity, is a hypothetical substance that possesses something truly bizarre: negative energy density. In the simplest terms, this means it would have a kind of repulsive gravity. While normal matter creates the attractive gravity that curves spacetime inward to form wells and depressions, exotic matter would curve spacetime outward, creating a kind of hill or anti-gravity effect. This property is absolutely crucial because it provides the counterpressure needed to prop open the throat of a wormhole or stabilize the warp bubble of an Alcubierre drive, preventing these intricate structures from instantly collapsing under their own intense gravitational forces. The very idea of negative energy density challenges the classical energy conditions that have long been cornerstones of physics. These conditions, like the weak and strong energy conditions, essentially state that energy density must always be non-negative and that gravity should always be attractive. Exotic matter violates these rules, yet, remarkably, quantum mechanics doesn't outright forbid its existence. In fact, quantum field theory suggests that on the tiniest of scales, the vacuum of space is not empty but seething with virtual particles that constantly flicker in and out of existence. These quantum fluctuations can create tiny regions of negative energy density. We have a real, albeit minuscule, laboratory demonstration of this in the Casimir effect. When two incredibly smooth, neutral metal plates are placed extremely close together in a vacuum, they experience a slight attractive force. Why? Because the space between the plates restricts the types of quantum fluctuations that can occur there, resulting in a lower energy density between the plates than in the surrounding space. This creates a pressure differential that pushes the plates together, providing tangible evidence that negative energy densities are not pure fantasy, but a real feature of our quantum universe. The monumental challenge, however, lies in the scale. The amounts of exotic matter generated by the Casimir effect are vanishingly small, existing for fleeting moments on a microscopic scale. To stabilize a traversable wormhole large enough for even a single particle, let alone a spaceship, the calculations show we would need astronomical quantities of this exotic substance, quantities that dwarf what we see in any known quantum effect and would require energy densities comparable to those found inside neutron stars. Furthermore, this exotic matter would need to be meticulously arranged and sustained, a feat of engineering so far beyond our current capabilities that it remains firmly in the realm of theoretical physics. This is the primary reason why such gravitational labyrinths are considered hypothetical. We lack not just the technology, but a complete understanding of how to generate and control the exotic matter they desperately need to exist. This quest for exotic matter intriguingly connects to one of the greatest mysteries in modern cosmology: dark energy. We know the universe's expansion is accelerating, driven by some unknown repulsive force that makes up about 68% of the universe's energy budget. One leading hypothesis is that dark energy is a manifestation of a cosmological constant, a uniform energy density permeating all of space that has a strong negative pressure. While not identical to the exotic matter needed for a wormhole, the repulsive gravitational effect of dark energy shows that nature might already be employing a form of anti-gravity on the largest scales imaginable. Researchers are actively exploring whether there could be a connection between these macroscopic vacuum fluctuations and the microscopic ones that generate the Casimir effect. Could understanding dark energy provide clues on how to manipulate energy densities on a smaller scale? It's a long shot, but it highlights how the most speculative ideas in physics are often intertwined with its most pressing unsolved problems. Without this exotic scaffolding, any attempt to create a wormhole or warp drive would be doomed to immediate failure. The immense positive energy and mass required to initially warp spacetime into such a complex labyrinth would, according to general relativity, inevitably cause it to collapse into a black hole or simply snap shut in an instant. The exotic matter acts as the essential counterweight, the anti-gravitational glue that holds the entire impossible structure together. It's what transforms a mathematical solution in Einstein's equations into a potentially stable physical reality. This makes the search for and understanding of exotic matter far more than an academic exercise. It is the key that could potentially unlock the door to these incredible gravitational labyrinths, turning them from science fiction into a future chapter of science itself. But what if the ultimate gravitational labyrinth wasn't just a trap for light in space, but a trap for time itself? This brings us to one of the most dizzying concepts in all of theoretical physics, closed time-like curves, or CTC. Imagine a path through the cosmos so warped that it not only bends back on itself in space, but actually loops back on itself in time. An object or a beam of light following this path could, in theory, embark on a journey and eventually return to the exact same moment and location from which it departed, effectively meeting its own past. This isn't mere science fiction. It's a direct, albeit deeply strange, consequence of the equations of general relativity when applied to the most extreme gravitational environments. These time loops emerge from specific mathematical solutions to Einstein's field equations. The Gödel metric, discovered by the brilliant logician Kurt Gödel, describes a rotating universe where the entire cosmos spins. In such a universe, if you were to travel far enough in a straight line, you would eventually return to your starting point not just in space but in time. More practically, the spacetime around a massively rotating Kerr black hole is so severely twisted by frame dragging that it could theoretically contain these closed paths. Even certain wormhole configurations, if stabilized by exotic matter, could be manipulated to connect 2 points in time as well as space, creating a gateway that leads directly to a moment in the past. These are the blueprints for nature's most confounding mazes, where the very arrow of time is no longer a straight line but a tangled coil. The immediate and obvious problem with such time loops is the parade of logical paradoxes they unleash. The most famous is the grandfather paradox. If you were to travel back in time and prevent your own grandfather from meeting your grandmother, you would ensure your own never being born, which would make it impossible for you to travel back in time in the first place. This creates an irresolvable logical inconsistency. Other paradoxes involve information. A physicist could go back and give their younger self the blueprint for a time machine, creating knowledge that appears from nowhere in a closed loop with no original origin. These aren't just fun puzzles for science fiction writers. They represent a fundamental challenge to our understanding of causality, the principle that cause must always precede effect, which is a bedrock assumption of all physics and indeed rational thought itself. Faced with these bewildering implications, physicists are deeply divided. Some, like the renowned Stephen Hawking, argued vehemently that closed time-like curves are simply mathematical artifacts with no physical reality. He proposed the chronology protection conjecture, which essentially suggests that the laws of physics, specifically the behavior of quantum fields, will always conspire to prevent time travel. Hawking postulated that any attempt to create a time machine would result in a runaway feedback loop of energy. perhaps a wall of radiation or a vacuum instability that would destroy the wormhole or warp the spacetime enough to shut down the time loop before it could ever be used. In his view, the universe has a built-in "do not disturb" sign on the past, protecting history from paradox. Others take a more open-minded, if cautious, view. They explore resolutions to the paradoxes, such as the idea that any actions taken in the past were always a part of history, meaning you could not change anything because your actions are what always happened. This is the self-consistency principle championed by physicists like Igor Novikov. In this view, the timeline is fixed and immutable. Any attempt to create a paradox would be physically forbidden by the laws of nature. You might be destined to travel back and become your own ancestor, with the timeline seamlessly weaving your arrival into its fabric. While this avoids logical contradiction, it paints a strangely deterministic picture of reality where free will becomes an illusion. Consider a thought experiment with light itself trapped in one of these temporal labyrinths. A single photon could, in principle, orbit a closed time-like curve an infinite number of times. From an outside perspective, this might create a bizarre signature, and seemingly infinite amount of energy concentrated in one point, or a particle that appears to exist in multiple places at once along its own history. If we could detect such a thing, it would be the ultimate signature of a gravitational labyrinth where not just space but time itself has been knotted into an impossible shape. This blending of deep philosophy with hard physics is what makes the study of CTCs so captivating. It forces us to confront the very nature of reality, causality, and the limits of our own understanding. As we grapple with these temporal twists, we naturally arrive at the next frontier, where the rules become even stranger. Yet for all their power to describe the universe on their own terms, both general relativity and quantum mechanics reach their absolute breaking point at the heart of a gravitational labyrinth, the singularity. This is the central crisis of modern physics. General relativity paints a picture of a point of infinite density where space-time curvature becomes infinite, and the laws simply cease to provide meaningful answers. Meanwhile, quantum mechanics, the wildly successful rulebook for the atomic and subatomic world, utterly refuses to play nice with this description. It abhors such infinities and uncertainties. This fundamental conflict means that to truly understand what happens to light and information at the final boundary of a black hole's trap, we need a more complete theory, a theory of quantum gravity that can marry the vast cosmic scale with the tiny quantum world. This clash of titans gives rise to one of the most famous and heated debates in modern physics, the black hole information paradox. It was ignited by Stephen Hawking's stunning realization that black holes are not completely black. Due to quantum fluctuations at the very edge of the event horizon, they should slowly radiate energy, a faint whisper of particles now known as Hawking radiation. This process suggests that a black hole could eventually evaporate, completely disappearing from the universe, and here lies the paradox. According to the core principles of quantum mechanics, information cannot be destroyed. The quantum information that describes every particle that fell into the black hole must be preserved, even if the black hole itself vanishes. But according to Hawking's original calculations, the Hawking radiation is random thermal noise, containing no information about what was consumed. If a black hole evaporates, the information it swallowed seems to be irrevocably lost, violating a foundational pillar of quantum theory. This is not some abstract puzzle. It strikes at the very heart of whether the universe is predictable and deterministic at a fundamental level. In the quest to resolve this paradox, physicists have proposed some truly radical ideas. One is the holographic principle, a concept that sounds like it's straight out of science fiction but is taken very seriously. It suggests that all the information describing a three-dimensional volume of space like the interior of a black hole might actually be encoded on a two-dimensional surface surrounding it, much like a hologram where a 3D image is stored on a flat sheet. In this view, the event horizon isn't just a point of no return. It's a vast, complex hard drive that stores every bit of information about everything that has ever fallen in. The light and matter trapped inside the gravitational labyrinth are not lost. Their data is simply projected from the boundary, preserving the information and potentially resolving the paradox. This principle profoundly suggests that our perception of a 3D universe might be a grand illusion emerging from a deeper, two-dimensional reality. Other theories offer their own dramatic reinterpretations of the labyrinth's core. String theory, for instance, proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. One string-based description of black holes suggests the classic picture of a singularity is wrong. Instead, a black hole might be a giant, fuzzy ball of these strings, a fuzzball. There is no sharp event horizon or point of infinite density. The entire interior is a tangled, quantum mechanical mess where the information of infalling matter is safely stored within the complex vibrations of the strings. In this model, there is no labyrinth with a bottomless pit because the pit is filled with a quantum substrate. Another startling proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, uneventful space that general relativity predicts. Instead, it must be a searing wall of unimaginably high energy particles that would instantly incinerate anything crossing it. This would solve the information paradox, but at a huge cost, violating Einstein's principle of equivalence, which states that free falling through an event horizon should feel like floating in empty space. What makes gravitational labyrinths so much more than a theoretical playground is that they provide a unique experimental testing ground. By studying the final orbits of light around a black hole, the photon sphere and the shadow it casts, we might gather clues that point toward one theory and away from another. For example, the precise way light flickers and echoes at the edge of an event horizon could, in theory, reveal whether space-time is smooth or fuzzy at the quantum level. The Event Horizon Telescope's image of M87 was a first step, but future more sensitive telescopes could potentially detect subtle signatures in the light that hint at these quantum gravitational effects. These impossible worlds, these ultimate traps for light, are therefore not just an endpoint for understanding, they are the very gateway. They force our most brilliant minds to invent new mathematics and conceive of reality in utterly new ways, all in pursuit of the universe's deepest secret, a single, unified theory that can explain gravity's maze from the smallest quantum flutter to the largest cosmic curve. But what if we could become the architects of our own gravitational labyrinths, not just passive observers of nature's creations? This brings us to one of the most thrilling and speculative ideas in all of theoretical physics, the Alcubierre warp drive. Conceived by Mexican physicist Miguel Alcubierre in 1994, this concept is a gravitational labyrinth of a very special kind, one designed not to trap but to transport. Imagine a spacecraft not by pushing through space with rockets, but by manipulating the very fabric of spacetime around it. The ship would sit motionless inside a bubble of flat, normal spacetime. Meanwhile, the bubble itself would be propelled by a remarkable mechanism. The spacetime immediately in front of the bubble would be massively compressed, pulling the destination closer, while the spacetime directly behind it would be radically expanded, pushing the point of origin further away. In essence, the ship wouldn't be moving faster than light through space. Instead, space itself would be moving faster than light, carrying the bubble and its passenger along for the ride. This clever loophole appears to sidestep Einstein's ultimate speed limit, as nothing within the bubble is actually breaking the cosmic speed limit. The engine required to create this incredible phenomenon is where we run into the same exotic ingredient we encountered with wormholes, matter with negative energy density. To form the warp bubble, you would need a ring of this exotic matter surrounding the spacecraft. Its repulsive gravitational effect would be what contracts spacetime at the front and expands it at the rear, creating the wave that the bubble surfs across the cosmos. Within this warp bubble, the behavior of light would be as bizarre as in any natural labyrinth. Light emitted from the ship forward would be severely blue shifted as it hits the compressed space ahead, while light pointed backward would be red shifted into oblivion by the expanding space behind. Furthermore, if the bubble were to somehow collapse during the journey, the light and radiation trapped within could be released in a catastrophic burst of energy. The interior of a stable warp bubble would be a self-contained pocket universe, a miniature gravitational labyrinth isolated from the outside cosmos, where the normal rules of causality and communication could be severely tested. When Alcubierre first published his idea, the energy requirements were, to put it mildly, astronomical. Initial calculations suggested you would need the negative energy equivalent of the mass of Jupiter, or even a large planet, to power a bubble just a few hundred meters across. This instantly relegated the concept to the realm of pure mathematical fantasy. However, the story didn't end there. In the decades since, other physicists have tinkered with the equations. Notably, a researcher named Harold "Sonny" White at NASA, at Johnson Space Center, proposed a different geometry for the warp bubble, changing its shape from a flat ring to more of a donut-like torus. This and other refinements have suggested that the energy requirements could potentially be lowered from a planetary scale to something more akin to the mass of a large spacecraft or even smaller. While still far beyond any conceivable technology, this shift made the idea feel slightly less impossible, moving it from the category of pure fantasy to extremely speculative physics. This theoretical work has captured the imagination of organizations like NASA, which has explored these concepts through its Advanced Propulsion Physics Lab, often nicknamed EagleWorks. While their experiments are incredibly modest, often focused on measuring tiny, disputed effects in quantum vacuum fluctuations, the goal is to probe the very foundations of whether manipulating spacetime for propulsion is even remotely possible. The challenges are, of course, monumental beyond description. Beyond the need for exotic matter, there are serious concerns about causality violation, the potential to generate lethal Hawking radiation at the front of the bubble, and the mind-boggling problem of how you would even begin to steer or stop such a craft. You wouldn't just be driving a car, you'd be manipulating the fundamental geometry of the universe itself. The true power of the Alcubierre metric and ideas like it lies not in their immediate feasibility, but in their incredible ability to inspire. They represent a breathtaking fusion of hard science and boundless imagination, showing how the principles of general relativity that create black holes and wormholes might one day be harnessed by an intelligent civilization. It transforms gravitational labyrinths from terrifying natural traps into potential tools for exploration, illustrating humanity's enduring desire to not just understand the cosmos, but to navigate its deepest mysteries on our own terms. This foray into engineering spacetime blurs the line between astrophysics and aspiration, proving that the study of these impossible worlds is as much about defining our future as it is about explaining the universe's present. While black holes and wormholes represent dramatic warps in spacetime, there exists another class of hypothetical object that could weave gravitational labyrinths of a far more subtle and intricate kind: cosmic strings. These aren't the strings of string theory, but rather gargantuan, incredibly thin filaments of pure energy, thought to have been forged in the searing heat of the universe's first moments after the Big Bang. Picture them as cosmic cracks or fissures in the fabric of spacetime, one-dimensional defects where the fundamental forces of nature underwent a traumatic phase transition as the universe cooled, much like cracks forming in ice as water freezes. A single cosmic string would be narrower than a proton, yet it could stretch across the entire observable universe, and its density would be almost unimaginable. A mere inch of its length might contain more mass than a whole mountain range on Earth. It is this combination of extreme density and needle-like thinness that allows them to warp spacetime in a uniquely bizarre way. The gravitational field around a cosmic string is profoundly different from that of a spherical object like a star or a black hole. Because it is effectively a one-dimensional line, it doesn't create a gravitational well that things fall into. Instead, it warps the geometry of space around it in a way that is flat but misshapen. The spacetime around a straight, static cosmic string is conical. A helpful analogy is to take a piece of paper and cut out a thin, pizza slice-shaped wedge. Now tape the remaining edges together. The surface is still flat. You can roll a marble across it in a straight line, but it now has a deficit angle. All the geometry is now squeezed into a smaller total area. This is what space around a cosmic string is like. For a light beam, this means that if it passes on opposite sides of the string, the two paths can be lensed toward each other. This wouldn't create a blurry image like a galaxy's lensing, but a perfectly sharp double image of the same background object, a cosmic mirage of incredible precision. The labyrinthine potential of these objects becomes truly fascinating if they aren't perfectly straight and static. A cosmic string under tension could vibrate, whip through space at tremendous speeds, or even form loops. A rapidly moving string could create fleeting, intense gravitational distortions, potentially focusing light from distant sources into brief, brilliant flashes or creating complex patterns of multiple images. If a string were to form a coiled knot, the spacetime around it could become an incredibly complex maze of gravitational lensing, with light paths twisting around the coils in ways that might temporarily trap photons or send them on immensely long detours before they finally escape in our direction. In such a configuration, a cosmic string would act less like a simple lens and more like a hall of mirrors built into the cosmos itself, a true topological labyrinth. The theoretical foundation for these objects is deeply tied to grand unified theories, which attempt to describe how the electromagnetic, weak, and strong nuclear forces were once a single force in the early universe. Physicists like Alexander Vilenkin at Tufts University were pioneers in working out the detailed gravitational effects of these spacetime defects. His work showed that a network of cosmic strings, if it existed, could have played a crucial role in the formation of the large-scale structure of the universe. The immense gravitational pull of these strings might have acted as scaffolding, attracting the primordial gas that eventually collapsed to form the first galaxies and clusters of galaxies. In this way, these hypothetical gravitational labyrinths could be the unseen architects of the entire cosmic web we observe today. Despite decades of searching, from looking for their unique double imaging signature in telescope surveys to hunting for their faint imprint on the cosmic microwave background, cosmic strings have never been directly observed. Their existence remains a compelling prediction of certain particle physics models, but not all. Yet, the fact that they are even conceivable expands our view of what form a gravitational labyrinth can take. They demonstrate that the universe's most extreme environments aren't limited to points of infinite density like black holes, but can also include incredibly dense, extended linear structures, flaws in the very crystal of spacetime that could, in their own subtle way, bend and trap the light that ventures too close to their enigmatic forms. Yet while cosmic strings remain a spectacular but unconfirmed possibility, we have already discovered a far more pervasive and tangible form of gravitational labyrinth that envelops every galaxy in the cosmos, the immense invisible halos of dark matter. These are not the sharply defined traps of a black hole or the theoretical tunnels of a wormhole. They are vast, diffuse, and subtle. Imagine a galaxy not as an isolated island of stars, but as a glittering city seen through a gently warped pane of glass. The glass itself is invisible, but its subtle distortions stretch and shear the city's image, blurring the light from the buildings behind it. This is the effect of a dark matter halo, a gravitational labyrinth so enormous and so pervasive that it bends the very fabric of spacetime on a colossal scale, guiding and trapping light in a statistical web across billions of light years. The key to understanding these halos lies in their nature. Dark matter does not emit, absorb, or reflect light, which is why it remains invisible to our telescopes. We cannot see it directly, but we can most definitely observe its gravitational influence. It is this gravity that holds galaxies together. Without the immense mass of its dark matter halo, a spinning galaxy would simply fly apart, its stars scattered into the void. This gravitational grip also bends the path of light passing through it, a phenomenon known as weak gravitational lensing. Unlike the strong lensing that creates dramatic Einstein rings around galaxy clusters, weak lensing is far more subtle. It doesn't create multiple images or perfect circles. Instead, it produces a tiny, coherent distortion, a slight stretching or shearing of the images of thousands or even millions of background galaxies. No single distorted galaxy provides conclusive proof, but by studying the patterns of distortion across enormous swaths of the sky, astronomers can statistically map the invisible mass responsible. It's like deducing the shape of a lens by carefully analyzing the distorted view through it. This mapping process has revealed that dark matter halos are not simple spheres. They form an intricate, web-like structure known as the cosmic web, with vast filaments connecting dense nodes where galaxies cluster. Within a single halo, the density of dark matter is highest at the center and gradually decreases outward, creating a smooth gradient of gravitational influence. Light from a distant quasar or galaxy traveling through this labyrinth doesn't get caught in a single, inescapable orbit. Instead, its path is minutely deflected countless times as it passes through this vast, uneven landscape of invisible mass. Over cosmological distances, these tiny deflections add up, creating a measurable statistical trap for light. The photon isn't permanently captured, but its journey is undeniably sculpted by the unseen architecture of the halo, a gentle but persistent guiding hand that demonstrates gravity's power even in its most distributed form. To unravel the secrets of this cosmic labyrinth, we need powerful new eyes on the sky. This is the primary mission of the European Space Agency's Euclid telescope, launched in 2023. Euclid is designed to perform the most extensive and precise weak lensing survey ever conducted. It will observe billions of galaxies across more than a third of the sky, measuring their shapes with exquisite accuracy to detect the faint imprints of dark matter's gravitational shear. By compiling this immense dataset, Euclid will allow scientists to create a three-dimensional map of the dark matter distribution in the universe with unprecedented detail. This isn't just about cataloging where the dark matter is, it's about understanding its fundamental properties. Does it interact with itself in ways other than gravity? How has its distribution evolved over cosmic time? The answers to these questions, written in the subtly bent paths of ancient light, could finally reveal the true identity of this mysterious substance that makes up 85% of the matter in the universe. This perspective fundamentally changes how we view gravitational labyrinths. They are not always the violent, extreme environments of a black hole's event horizon. They can be vast, quiet, and almost imperceptibly gentle, yet their cumulative influence is arguably far greater. The dark matter halo surrounding our own Milky Way is a perfect example, a massive, sprawling structure that we are embedded within, its gravitational currents silently guiding the motion of stars and the path of light, all while remaining completely invisible to our direct sight. It is a labyrinth we live inside, one that defines the large-scale structure of the entire cosmos. This realization that the most common gravitational traps are not the dramatic singularities but these pervasive, statistical webs, leads our curiosity naturally toward environments where invisible mass creates far more active and energetic phenomena. Now consider the most energetic and chaotic gravitational labyrinths in the known universe, the blazing hearts of active galaxies. At the core of these cosmic powerhouses lies a supermassive black hole, but not a quiet, dormant one. This is a black hole in the midst of a ferocious feast, surrounded by a vast, swirling whirlpool of superheated gas and dust known as an accretion disk. As this material spirals inward at velocities approaching the speed of light, it is compressed and heated to millions of degrees, transforming the galactic center into a colossal engine that can outshine its entire host galaxy. This phenomenon is what astronomers call an active galactic nucleus, or AN. When such an object is positioned so that its brilliant core is directly visible from Earth, we often classify it as a quasar, a point of light so luminous it can be seen across billions of light years. Within these environments, the gravitational labyrinth is not a quiet, static trap. It is a seething, turbulent maelstrom where gravity, magnetism, and raw energy collide in an epic struggle. The dynamics within an accretion disk are a physicist's dream and nightmare. The primary force shaping this structure is, of course, the immense gravity of the central black hole. But the material in the disk doesn't simply fall straight in. It orbits at fantastic speeds, with inner regions whirling around much faster than outer ones. This differential rotation creates immense friction and magnetic fields that become twisted into coils of unbelievable power. These magnetic fields can actually extract energy from the black hole's spin and funnel some of the infalling material away from the poles at nearly the speed of light, creating spectacular jets that extend for thousands of light years into intergalactic space. For light trying to navigate this environment, the journey is perilous. A photon emitted from the inner disk is subject to extreme Doppler shifting, its color dramatically blue shifted if it's beamed toward us from an approaching part of the disk, or red shifted if from a receding portion. It must also contend with the intense gravitational redshift as it climbs out of the black hole's deep potential well, and there's a high probability it will be absorbed and re-emitted multiple times by the thick, swirling plasma before it ever escapes. This chaotic path creates a complex and variable emission signature that tells the story of its turbulent origin. Our understanding of these cosmic power plants has been revolutionized by space-based observatories like the Chandra X-ray Observatory and the Hubble Space Telescope. Chandra, designed to see the high-energy X-ray universe, peers directly into the inner sanctum of AGN. X-rays are typically generated in the hottest regions closest to the black hole, often in a corona of energetic particles above the disk. By analyzing these X-rays, astronomers can probe the conditions just outside the event horizon. Hubble, with its exquisite resolution, has captured stunning images of the jets erupting from quasars and the brilliant cores of active galaxies, often revealing how they interact with and shape their host galaxies. The combination of data across the electromagnetic spectrum, from radio waves emitted by the jets to gamma rays from the most energetic processes, allows scientists to build a complete picture of these complex systems. They serve as unparalleled natural laboratories for studying physics under conditions of extreme density, temperature, and gravity that we could never hope to recreate on Earth. Perhaps the most crucial information carried by the light that finally escapes this gravitational maze is the fingerprint of the black hole itself. The precise way the emission lines in the spectrum are broadened and shifted reveals the incredible velocities within the accretion disk, which in turn allows astronomers to calculate the black hole's mass. Even more remarkably, the properties of the X-ray emission can be used to gauge the black hole's spin. A rotating Kerr black hole drags spacetime around with it, allowing material to orbit much closer to the event horizon than around a non-spinning black hole. The inner edge of the accretion disk is therefore a direct indicator of spin. By carefully analyzing the light that has navigated the intense gravitational and magnetic fields near this edge, scientists can determine if the black hole is spinning slowly, rapidly, or not at all. This makes every AGN and quasar a cosmic beacon, broadcasting details about the nature and history of the supermassive black hole powering it across the vast expanses of the universe. But what if the gravitational labyrinths we've explored so far are merely the ones we can perceive, confined as we are to the 3 dimensions of space and 1 of time? This brings us to one of the most expansive and mind-stretching ideas in modern theoretical physics: the possibility that our entire universe is just one membrane, or brane, floating within a higher dimensional reality, and that other, parallel universes might exist on other branes, each with their own unique physical laws and potentially their own unimaginable gravitational mazes. In this breathtaking vision of the cosmos, known as the Braneworld scenario, the true nature of gravity and the ultimate form of a labyrinth might be hidden from us in dimensions we cannot directly access. The foundation for this idea comes largely from string theory, which proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. For the mathematics of string theory to work consistently, it requires more than the 4 dimensions we experience, often 10 or even 11. The Braneworld concept provides a compelling way to explain why we don't perceive these extra dimensions. Our entire universe might be trapped or localized on a 3-dimensional brane, while gravity, unlike the other forces, is free to propagate through the full higher dimensional bulk space. This means the gravitational labyrinths we observe, the warped spacetime around black holes, and the bending of light might be just a shadow, a lower dimensional projection of far more complex and intense structures playing out in a reality with more spatial dimensions. One of the most profound theoretical discoveries in this area is the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. This is a concept so powerful it's been called a university in a box. In simple terms, it proposes a duality, a complete equivalence between a theory of gravity in a certain type of higher dimensional space, anti-de Sitter space, and a quantum field theory without gravity that lives on its lower dimensional boundary. This means that a gravitational phenomenon like a black hole trapping light in a 5-dimensional bulk could be perfectly described by a complex, hot soup of interacting particles on a 4-dimensional boundary. It suggests that the light trapped in a higher dimensional gravitational labyrinth might manifest to us, stuck on our brane, not as a distorted image, but as a specific kind of thermal energy or information entropy in a quantum system. This isn't just a mathematical curiosity. It provides a potential toolkit for understanding the infamous black hole information paradox by recasting a gravitational mystery in the language of quantum physics. Theorists like Lisa Randall of Harvard University have taken these ideas and run with them, constructing concrete and testable models. Along with her collaborator Raman Sundram, she developed the Randall-Sundram model, which elegantly uses a warped extra dimension to explain one of physics' most nagging problems, the hierarchy problem, or why gravity is so incomprehensibly weaker than the other fundamental forces. In their model, our universe is a brane where the quantum fields of the standard model are trapped, but gravity is diluted because it leaks into an extra dimension. A gravitational labyrinth, like a black hole, could form in that extra dimension, and its influence could subtly affect our brane. Randall has even explored the possibility that the dark matter permeating our galaxy could actually be ordinary matter trapped on a parallel shadow brane very close to our own, its presence only revealed to us through its gravitational tug, a truly cosmic-scale labyrinth hidden in plain sight. This expansion into multidimensional thinking inevitably leads to a thrilling question. If these extra dimensions and parallel branes exist, how could we ever hope to detect them? One promising avenue is through their gravitational footprints. A massive object moving or oscillating in a higher dimension could create tiny ripples or anomalies in gravity within our own brane that might be detectable with incredibly precise instruments. Another idea involves looking for tiny deviations in how gravity behaves at very small, sub-millimeter scales, where the influence of extra dimensions might become significant. Even the behavior of light itself could be a clue. If a photon were to occasionally skip into an extra dimension, it might appear to us as if a tiny amount of energy has mysteriously vanished from a closed system. While no definitive evidence has been found, these thought experiments transform the search for gravitational labyrinths from a study of what we can see to a detective story about what must be lurking just beyond our current perception, urging a fundamental rethink of where and how the universe hides its most impossible secrets. But if we want to understand gravity at its most fundamental level, we must venture from the vast cosmic scale of dark matter halos down to the very fabric of spacetime itself, to a realm so small it defies imagination. This is the domain of quantum foam, a concept so bizarre it suggests that if we could peer down at the Planck scale, a distance of 10 to the minus 35 meters, the smooth, continuous spacetime described by Einstein would dissolve into a seething, turbulent froth. Picture the surface of a boiling ocean during a storm, with bubbles constantly forming, merging, and popping. Now imagine that instead of water, it's the very stage upon which the universe plays out. This is quantum foam, a chaotic, probabilistic foam where spacetime itself loses its definite geometry and fluctuates wildly, creating a labyrinth of unimaginably small, fleeting gravitational twists and turns. This revolutionary idea was first proposed by the brilliant physicist John Wheeler in the 1950s. He realized that the marriage of quantum mechanics with general relativity would have profound implications for the nature of spacetime. The Heisenberg uncertainty principle, which tells us we cannot precisely know both a particle's position and its momentum at the same time, should also apply to the gravitational field itself. At these minuscule scales, the energy of the vacuum is constantly fluctuating. According to Einstein's own equations, energy tells spacetime how to curve. Therefore, these random quantum fluctuations must cause spacetime itself to writhe and curve erratically. For an instant, a tiny region of space might curve into a microscopic wormhole, only for it to collapse a moment later. Another fluctuation might create a minute black hole that evaporates instantly via Hawking radiation. In this frantic dance of creation and annihilation, spacetime is not smooth. It is a probabilistic foam, and within its churning structure, countless transient gravitational labyrinths are born and die in a fraction of a nanosecond. For a photon traveling across the universe, this has a fascinating, albeit minuscule, implication. Light always takes the shortest path between 2 points, but if the very fabric of space is frothy and uncertain, what does shortest path even mean? Its journey would not be a straight, clean line. Instead, it would be a walk through an endlessly shifting maze. Over a very small distance, the path of a light particle would jitter and wobble as it navigates these random spacetime fluctuations. Over a vast cosmic distance, these tiny, unpredictable deviations could, in theory, add up. It suggests that there is a fundamental limit to how precisely we can measure the position of any object, not because of our instruments' limitations, but because of the inherent fuzzy geometry of the universe itself. The speed of light itself, that universal constant, might even experience immeasurably tiny variations in this foamy medium, though its average value would remain constant over large distances. Modern theories of quantum gravity, like loop quantum gravity, have built upon Wheeler's intuitive picture. This approach proposes that spacetime is not continuous but is actually composed of discrete, tiny loops, a fabric woven from individual threads at the Planck scale. In this view, the quantum foam is not just a random fluctuation, but has a specific granular structure. These loops can become tangled and interconnected, creating a complex network that again suggests a foamy, labyrinthine structure at the foundation of reality. While the math is incredibly complex, the core idea remains. On the smallest possible scale, the smooth, warped spacetime of black holes and dark matter halos gives way to a turbulent, uncertain sea of geometry where the very concepts of before and after can become blurred. The challenge, of course, is that this ultimate miniature labyrinth is currently far beyond any possibility of direct observation. The energy and scale required to probe the Planck length are far greater than anything our particle colliders can achieve. Yet the concept of quantum foam is far from irrelevant. It represents the final frontier in our quest to unify gravity with quantum mechanics. It is the logical endpoint of applying quantum rules to the gravitational field, and it beautifully illustrates the universality of gravitational mysteries. From the largest cosmic web woven by dark matter to the tiniest, most fleeting fluctuations in the vacuum, gravity creates labyrinths at every scale, binding the cosmos together in a web of curvature that is both immense and infinitesimal. But if black holes represent the ultimate endpoint of gravitational collapse, neutron stars are nature's way of showing us just how extreme things can get without crossing that final threshold. These incredible objects are the collapsed cores of massive stars that went supernova but weren't quite heavy enough to form a black hole. Imagine taking the mass of our entire sun and crushing it down into a sphere no larger than a city, about 12 miles across. The density is almost incomprehensible. A single sugar cube-sized piece of neutron star material would weigh as much as a mountain, roughly 1 billion tons on Earth. This insane density creates a gravitational field at the surface about 200 billion times stronger than Earth's, a force second only to that of a black hole itself. Light emitted from the surface of a neutron star pays a heavy price for escaping this gravitational well. It undergoes severe gravitational redshift, losing a significant amount of energy as it climbs away, which makes it appear much redder and dimmer to an outside observer than it actually is at the source. Yet despite this immense gravity, light is not permanently trapped. This is because neutron stars, unlike black holes, possess a solid and unimaginably hard surface. There is no event horizon, no true point of no return. This critical difference makes them extraordinary natural laboratories. We can observe phenomena at their surfaces and in their magnetospheres, receiving light that has battled against but ultimately escaped an intense gravitational field. This allows us to test the predictions of general relativity in what is called the strong field regime, where gravity is incredibly powerful but not infinite. It's like having a black hole's doorstep to study without the door being permanently shut. The paths of light are dramatically curved as they leave the star, but they are not closed loops. They always find a way out, carrying with them invaluable data about the conditions they endured. The complexity doesn't end with gravity. Neutron stars often possess the most powerful magnetic fields in the known universe. For a class of them known as magnetars, these fields can be 1,000 trillion times stronger than Earth. These ferocious magnetic fields twist the environment around the star into a complex, dynamic labyrinth of their own, channeling particles and radiation into powerful beams. This leads to one of the most famous and useful phenomena in all of astronomy, pulsars. A pulsar is a rapidly rotating neutron star that beams radiation from its magnetic poles. If this beam sweeps across Earth like a cosmic lighthouse, we detect a perfectly timed pulse of radiation with every rotation. These pulses can be as regular as the most precise atomic clocks, and the fact that we can detect them at all is a testament to the power of these beams to overcome the star's immense gravitational pull. They are brilliant lighthouses whose light successfully navigates a gravitational and magnetic maze to reach us across thousands of light years. A monumental leap in our understanding came from the landmark observation of a neutron star merger in 2017, an event known as GW 170,817. Detected first as gravitational waves by the LIGO and Virgo observatories, and then almost immediately afterward by telescopes across the entire electromagnetic spectrum. This event was a watershed moment for multi-messenger astronomy. The collision of these two ultra-dense objects created ripples in spacetime itself, and also produced a spectacular kilonova explosion, a forge for heavy elements like gold and platinum. The observations provided direct, simultaneous insight into both the gravitational dynamics of the merger and its luminous aftermath. It confirmed predictions about how such an event would unfold and gave us unprecedented data on the behavior of matter and gravity under the most extreme conditions imaginable outside a black hole. Studying neutron stars gives us a unique and precious window into physics we can never replicate on Earth. They are objects on the very brink of becoming full gravitational labyrinths, teetering on the edge of collapse but still allowing information to escape. They let us probe the equation of state of ultra-dense matter, how matter behaves when squeezed to such incredible degrees, and test the limits of general relativity in an environment that is both accessible and extreme. By analyzing the timing of pulsar beams and the light from their surfaces, we are effectively conducting precision experiments on some of the most bizarre and powerful objects in the cosmos, all from the safety of our own solar system. They represent a perfect middle ground, a natural stepping stone that deepens our understanding of gravity's power and naturally leads our curiosity to wonder if we could ever create such phenomena ourselves. The audacious question arises: if nature can forge black holes and cosmic strings into gravitational labyrinths, could humanity ever learn to build its own? This leap from cosmic observer to cosmic architect is the stuff of supreme science fiction, yet it is not entirely dismissed by the stern rules of physics. The theoretical blueprints already exist, scattered across the pages of advanced general relativity and quantum field theory. One of the most discussed ideas involves creating an artificial analog of a Kerr black hole, not by crushing stellar amounts of matter, but by using exotic states of matter to mimic its spacetime bending properties. Some researchers speculate that certain metamaterials, engineered substances with properties not found in nature, could be designed to manipulate light in a way that replicates the effects of a curved spacetime. In a lab, such a device wouldn't create real gravity, but it could force light to follow the same twisted paths it would take around a rotating black hole, effectively constructing a tabletop gravitational labyrinth for study. The energy requirements for creating a real gravity-based labyrinth are, to put it mildly, astronomical. To warp spacetime in any significant way requires concentrations of mass or energy that dwarf our entire planetary civilization's output. Creating even a microscopic transient singularity, a true point of infinite density, is far beyond any foreseeable technology, not to mention the terrifying challenge of containing and controlling it. The power needed to sustain an Alcubierre warp bubble or a Morris Thorne wormhole, as we've discussed, involves generating and manipulating astronomical quantities of exotic matter with negative energy density. Our current glimpse of such effects, like the minuscule negative energy observed in the Casimir effect, is trillions upon trillions of times too weak to be of any practical use. The engineering hurdles are so profound that they push the concept from the realm of extremely difficult into the category of what might be forever physically impossible. This immediately forces us to confront a host of serious ethical and safety considerations. The very nature of a gravitational labyrinth is to trap things: light, matter, information. An artificial creation, especially one based on a real singularity, would carry an inherent and potentially existential risk. What if the containment mechanism failed? A microscopic black hole, for instance, could theoretically evaporate via Hawking radiation, but if it were even slightly stable, it could begin accreting matter from its surroundings, sinking into the Earth and growing uncontrollably with catastrophic consequences. Even a controlled experiment could have unforeseen side effects, perhaps creating unpredictable spacetime instabilities or regions where causality breaks down. The development of such technology would demand an unprecedented level of international oversight and a rigorous framework for safety, akin to the protocols for handling world-ending pathogens or antimatter, but on a scale we can barely conceive. Futurists and physicists are deeply divided on the feasibility of such projects. Some, inspired by the words of science fiction legend Arthur C. Clarke that any sufficiently advanced technology is indistinguishable from magic, see these as the ultimate engineering challenges for a future, star-faring civilization. They argue that what seems impossible today might be a textbook problem for our descendants millennia from now. Others maintain a more skeptical view, arguing that the laws of physics themselves may erect fundamental barriers that no amount of technological advancement can overcome. The need for exotic matter, the incredible energy costs, and the potential for universe-altering paradoxes might place artificial gravitational labyrinths permanently off-limits, a frontier we can explore only through mathematics and simulation, never with actual hands-on construction. This drive to create speaks to something fundamental in the human spirit, our desire not just to understand the universe, but to interact with it, to shape it, and to test its limits. While building a full-scale gravitational trap may remain a dream, the pursuit itself pushes our technology in unexpected directions. The research into metamaterials for cloaking devices or advanced propulsion concepts has valuable spin-offs in materials science, quantum computing, and energy research. By aiming for the stars, we often develop the tools that improve life on Earth. This speculative journey ensures that we continue to ask the biggest questions. keeping our collective imagination alive and driving the endless human quest for knowledge and mastery over the physical world. While we can observe the distorted light escaping these cosmic mazes and theorize about their hidden structures, a completely new window into gravitational labyrinths opened in 2015, one that allows us to literally feel their vibrations. This revolutionary tool is the detection of gravitational waves, ripples in the fabric of spacetime itself, first predicted by Einstein a century ago. Think of spacetime not just as a static rubber sheet, but as a vast, calm pond. When a massive object moves through it, particularly one with intense gravity, it doesn't just create a stationary dent, it sends out waves, much like a boat moving across the water. Now imagine two black holes, each an ultimate gravitational labyrinth, locked in a final, death spiral dance before merging into one. Their incredible mass and acceleration don't just bend light, they violently shake the very foundation of reality, sending out these ripples that travel across the universe at the speed of light, carrying with them the unique signature of the cataclysm that created them. The first direct detection of these waves on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, or LIGO, was a landmark moment in human history. The signal, designated GW 150,914, was the faint chirp of two black holes, one about 36 times the mass of our Sun and the other 29, colliding over 1 billion light-years away. By the time these waves reached Earth, they were vanishingly small, stretching and squeezing the 4-kilometer-long arms of the LIGO detectors by less than 1,000th the width of a proton. The beauty of this signal lies in its information. By analyzing the precise shape and frequency of the gravitational wave chirp, scientists could extract astonishingly detailed information about the system that created it. They determined the masses of the two black holes, measured their spins, and even confirmed that the final merged object was indeed a black hole, ringing down like a bell to settle into a new, quiet state. This was our first direct proof that black holes not only exist but can pair up and merge. For the study of gravitational labyrinths, this is transformative. These waves give us a direct probe into the dynamics of spacetime in its most extreme state, right at the edge of the event horizon. The final moments of a black hole merger are a violent shaking of the labyrinth's very walls. Theorists suggest that the vibrations of the newly formed black hole, captured in the gravitational wave signal, might even carry subtle imprints of the photon sphere, that region of trapped light quivering under the impact. Future, more sensitive detectors might be able to discern these finer details, allowing us to map the geometry of spacetime around a black hole with precision, all without seeing a single photon. It's like learning the entire shape of a bell just by listening to its ring in a dark room. The future of this new sense is even more exciting. While LIGO detects high-frequency waves from stellar mass black holes and neutron stars, the Laser Interferometer Space Antenna, or LISA, is a planned European Space Agency mission that will open up a new low-frequency band. Consisting of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, LISA will be sensitive to the gravitational waves from the mergers of supermassive black holes, the monsters weighing millions or even billions of solar masses that lurk at the centers of galaxies. The collisions of these behemoths will create waves that can oscillate for years, containing a wealth of information about their history and environment. Furthermore, LISA could potentially detect even more exotic sources, such as the gravitational background hum from cosmic strings, those hypothetical spacetime defects, if they snap or vibrate, or the faint signal from a source falling into a wormhole, an event that would leave an unmistakable signature in the waves. This method of listening to the universe provides a completely independent and complementary way to explore these impossible worlds, one that is untouched by the obscuring effects of dust or gas that can block light, allowing us to probe deeper into the gravitational shadows than ever before. Now, imagine if we could turn the very fabric of these gravitational labyrinths into a giant cosmic recording device, one that captures and replays light itself to reveal the hidden structure of spacetime. This isn't science fiction, it's the remarkable reality of light echoes. When a brilliant, sudden flash of light erupts from an event like a supernova or a stellar flare, that light doesn't just travel directly to our telescopes. It also floods out in all directions, illuminating vast clouds of interstellar dust and gas, or even warping around the curved spacetime near massive objects. Some of this light takes a direct path to us, but a significant portion hits these cosmic obstacles and scatters, bouncing off and taking a much longer, detoured journey before finally arriving at our detectors, sometimes years or even decades later. This delayed signal is the echo, a ghostly afterimage that allows us to see the same event multiple times and from different angles, effectively turning the universe into a natural echo chamber for studying gravity's most subtle effects. One of the most stunning examples of this phenomenon was the light echo from supernova 1987A, the closest stellar explosion observed in modern times. When it first lit up the sky in 1987, telescopes around the world captured the initial, brilliant flash, but the story didn't end there. In the years that followed, astronomers watched in awe as expanding rings of light, like ripples in a pond, seemed to emanate from the blast site. These weren't actual shockwaves moving through space, they were light echoes. The initial ultraviolet flash from the supernova had traveled outward, eventually reaching a large, pre-existing shell of dust located light years away from the explosion. As this light hit the dust, it was reflected toward us, creating the illusion of an expanding ring. By meticulously measuring the time delay and the geometry of these echoes, scientists could perform a kind of cosmic triangulation, precisely mapping the three-dimensional structure of both the dust cloud and the material ejected by the supernova itself, gaining insights that would have been impossible from the initial flash alone. When we apply this concept to the vicinity of gravitational labyrinths like black holes, the echoes become even more powerful diagnostic tools. Consider a flickering flare of light from the hot, chaotic accretion disk around a supermassive black hole. Some photons will come straight to us. Others, however, will have their paths dramatically bent by the black hole's immense gravity. They might loop around the backside, skim the photon sphere, or even get lensed around the entire object before finally being deflected in our direction. This creates a distinct echo. The main flare arrives first, followed by a delayed series of fainter copies that have taken these scenic routes through the warped spacetime. By carefully analyzing the timing and intensity of these delayed photons, astronomers can literally map the geometry of the spacetime around the black hole. It's akin to a bat using echolocation to navigate a dark cave. By listening to the returning echoes of light, we can paint a picture of the invisible structures, the event horizon, the photon sphere, the accretion disk, that define the gravitational maze. This technique has moved from theoretical curiosity to practical application with observatories like NAS, a neutron star interior composition explorer, or NICER, mounted on the International Space Station. NICER is designed to collect X-rays from neutron stars and black holes with incredible precision. By observing the rapid flickering of X-rays from an active black hole system, it can detect the minute delays between the initial flare and its gravitationally lensed echoes. The precise pattern of these delays is like a unique fingerprint that depends entirely on the mass and spin of the black hole and the precise layout of its surrounding environment. It provides a direct, observational test of general relativity's predictions in these extreme regimes, offering an independent method to measure black hole properties that complements other techniques like studying gravitational waves. Beyond single objects, light echoes can also reveal the large-scale gravitational labyrinth of the cosmic web. The light from a distant quasar can be lensed and delayed not just by one galaxy, but by multiple galaxies and dark matter halos along its path to Earth. This creates a complex pattern of multiple images and time delays, a phenomenon known as strong gravitational lensing. By measuring the different arrival times of these quasar images, which can vary by days or weeks, astronomers can not only map the distribution of the lensing mass, but also measure the expansion rate of the universe itself. Each delayed image is a probe, its travel time affected by the total amount of matter and energy it has passed through, making light echoes a crucial tool in cosmology for weighing the invisible components of our universe. What makes this method so revolutionary is that it transforms passive observation into active interrogation. We are no longer just waiting for light to arrive. We are using the universe's own infrastructure to conduct experiments. A single flash of light becomes a probe that scatters through a gravitational maze, and its returning echoes tell us about every twist and turn it encountered along the way. This data is invaluable, but it is also incredibly complex to decipher. The subtle patterns hidden within the light curves require sophisticated models to interpret, which is why this observational technique is so deeply intertwined with the next step in our exploration, using the raw power of supercomputers to simulate these impossible environments and predict what echoes we should be listening for. But how do we move from these brilliant but indirect observations to a true understanding of what's happening deep within these gravitational vortices? We turn to the incredible power of supercomputers, creating digital laboratories where we can experiment with the fabric of spacetime itself. This field, known as numerical relativity, is the art of taking Einstein's immensely complex equations and solving them not with pen and paper, but with brute computational force, one tiny calculation at a time across thousands of processors working in concert. It allows us to create breathtakingly detailed simulations of black holes, neutron star mergers, and wormholes, visualizing the flow of light and matter through these cosmic mazes in ways we could never hope to observe directly. These aren't just animated guesses, they are rigorous mathematical experiments that predict how spacetime will curve, twist, and ripple under the most extreme conditions imaginable. A leader in this field is the Simulating E-Extreme Spacetimes, or SXS, collaboration. This project brings together physicists and computer scientists to solve Einstein's equations for some of the most violent events in the universe. Their work was instrumental in helping the LIGO collaboration know what gravitational wave signals from merging black holes should look like, creating waveform templates that were essential for picking that first faint chirp out of the noise. But their simulations go far beyond just the gravity. They also model the behavior of magnetized plasma in accretion disks and the intricate paths of photons. By tracing the journey of millions of virtual light particles through their simulated warped spacetime, they can produce stunning visualizations that show us what an accretion disk would truly look like if we could see it up close, complete with the Doppler shifts, gravitational lensing, and the dark shadow of the black hole's event horizon. These visualizations were the scientific backbone for the black hole imagery in the film Interstellar, making the fictional portrayal as accurate as current science would allow. The challenges these simulations face are as immense as the phenomena they seek to model. The equations of general relativity are notoriously difficult to solve, especially in dynamic situations where spacetime is violently changing. To avoid the mathematical infinities that arise at the center of a black hole singularity, simulations often use clever coordinate systems that effectively slow down time near the event horizon, allowing them to evolve the rest of the system without getting stuck. Incorporating the effects of magnetic fields and the complex physics of plasma adds another layer of extreme difficulty, requiring a delicate dance between different sets of physical laws. And perhaps the greatest frontier is the incorporation of quantum effects, simulating what happens at the quantum level at the edge of a singularity is a problem that currently sits at the very limits of our computational and theoretical understanding. Yet, despite these challenges, the payoff is immense. These digital explorations are more than just pretty pictures. They serve as crucial guides for observational astronomy. A simulation might predict a specific flickering pattern in the light from a black hole's corona, or a particular ring-down signal in gravitational waves after a neutron star collision. Astronomers can then take these predictions and scour their telescope data, looking for these telltale signatures. In this way, numerical relativity doesn't just follow observation. It leads it, telling us where and what to look for in the vast, noisy cosmos. It turns the universe into a puzzle where we can test our theories by comparing the output of our computers against the data from our most powerful telescopes, creating a powerful feedback loop between digital discovery and real-world observation. This computational approach effectively grants us a safe, virtual playground for testing ideas that would otherwise be pure speculation. Want to see what happens if two wormholes collide? We can simulate it, curious about the stability of a warp drive bubble, run the numbers. These virtual experiments allow us to explore the consequences of our theories without any physical risk, revealing which ideas lead to logical contradictions or mathematical impossibilities, and which might just be possible within the laws of physics. As our computing power grows exponentially and our algorithms become more sophisticated, the line between simulation and reality begins to blur. The digital black holes we create are becoming so physically accurate that they are, in a very real sense, functional duplicates of the real thing, allowing us to explore their secrets from the inside out without ever leaving Earth. But as we chart these cosmic mazes and decode the behavior of trapped light, we are inevitably drawn from the realm of pure physics into much deeper waters questions that have puzzled philosophers for millennia. What does the existence of such impossible structures say about the fundamental nature of reality itself? If regions of spacetime can twist back on themselves to form closed loops, where an effect could theoretically precede its cause, what becomes of our understanding of free will, destiny, and the very arrow of time? Gravitational labyrinths force us to confront the possibility that causality, the bedrock of rational thought and scientific inquiry, might not be the immutable law we believe it to be, but rather a local condition that breaks down in the universe's most extreme environments. This isn't just a technical problem for physicists. It's a profound philosophical challenge that strikes at the heart of how we perceive our place in the cosmos. The ethical dimensions of this knowledge are equally staggering to consider. If humanity ever advanced to the point where we could create or stabilize a wormhole, the potential for misuse would be as immense as the technological achievement itself. Such a power could redefine everything from warfare and geopolitics to economics and social structure. Imagine a world where a privileged few could access shortcuts through spacetime, creating unimaginable inequalities or even wielding the power to manipulate history itself. The ethical frameworks we have today, built upon a stable and linear progression of cause and effect, would be completely inadequate. We would need a new branch of ethics, cosmic ethics, perhaps, to grapple with responsibilities that extend across time and space, considering the well-being of future generations and even past ones, in a universe where those distinctions could blur. The very act of creating a traversable labyrinth could have unforeseen consequences for the stability of spacetime itself, imposing a moral duty of caution that dwarfs any technological challenge we've ever faced. Philosophers like Nick Bostrom have already laid some groundwork for this kind of thinking with his simulation hypothesis, which asks whether our reality might be an artificial construct. While distinct from gravitational physics, this idea shares a common thread. It forces us to question the nature of our reality and the limits of what we can truly know. If our universe can contain structures as bizarre as closed time-like curves, how can we be certain that our perception of a consistent, logical cosmos isn't just a convenient illusion, a limited view from within a much larger and stranger system? Bostrom's work reminds us that our cognitive and sensory apparatus evolved to survive on the African savanna, not to comprehend the infinite intricacies of warped space-time. There may be fundamental aspects of the universe, like the true nature of a singularity, that are forever beyond the grasp of human understanding, existing in a category of the unknowable. This journey into gravitational labyrinths ultimately holds up a mirror to humanity itself. Our relentless drive to explore these impossible worlds speaks to a deep-seated need to find meaning, to push boundaries, and to understand the stage upon which our existence plays out. The cultural resonance of these ideas, from ancient myths about underworlds to modern science fiction, shows that they tap into something universal within the human psyche. They represent the ultimate challenge, the final frontier of knowledge, but they also teach us humility, confronting the sheer scale and complexity of the cosmos and the bizarre physics that governs it can be a deeply humbling experience that puts our earthly concerns into a grander cosmic perspective. It fosters a sense of awe and wonder that is as valuable as any scientific discovery, enriching the human experience and reminding us that the universe is far more strange and wonderful than we could ever have imagined. These mind-bending concepts of trapped light and gravitational labyrinths have not remained confined to academic journals. They have exploded into our collective imagination through the powerful mediums of literature and film, shaping how society views the deepest mysteries of the cosmos. Science fiction has long served as a bridge between complex theoretical physics and the public's sense of wonder, taking ideas that might otherwise seem abstract and giving them a narrative heartbeat. A pivotal early example is Carl Sagan's seminal novel, Contact, where the protagonist, Ellie Arroway, travels through a series of wormholes constructed by an advanced alien civilization. Sagan, an astrophysicist himself, was deeply committed to scientific plausibility. When developing the wormhole concept for the book, he consulted his friend and colleague Kip Thorne to ensure the idea wasn't pure fantasy. Thorne's initial calculations confirmed that a traversable wormhole would require exotic matter, a concept that, while hypothetical, was grounded in the equations of general relativity. This collaboration between scientist and storyteller set a new standard, proving that compelling fiction could also be respectful of scientific principles, and it inspired a generation of readers to look up at the night sky with a more informed sense of curiosity. This feedback loop between science and cinema reached its zenith with the 2014 film Interstellar, directed by Christopher Nolan. The movie's breathtaking depiction of a supermassive rotating black hole named Gargantua and its accompanying wormhole was not merely artistic license. It was the product of a year-long collaboration with Kip Thorne, who served as both executive producer and scientific advisor. Thorne provided the visual effects team at Double Negative with a set of complex equations governing gravitational lensing and the behavior of light around a Kerr black hole. The team then built a new, custom renderer that physically simulated the path of millions of light rays through this warped spacetime, rather than simply animating what they thought it should look like. The result was the first scientifically accurate visualization of a black hole, complete with the accretion disk lensed into a shimmering halo around the dark shadow of the event horizon. Astonishingly, the visual effects work led to new scientific insights. The team discovered that the high-speed rotation of the accretion disk would cause the light to create multiple, stacked images around the black hole, a detail that was later published in a peer-reviewed paper. This perfect synergy transformed public perception, making the once esoteric idea of a photon sphere and warped light tangible and visually spectacular for millions of viewers worldwide. The cultural impact of these portrayals is profound and multifaceted. They do more than just entertain. They shape aspirations and fuel the scientific ambitions of future generations. A student watching Interstellar or reading Contact isn't just seeing a cool special effect. They are being introduced to complex ideas like time dilation, higher dimensions, and the five-dimensional bulk in a visceral, memorable way. This exposure demystifies advanced physics and makes it accessible, often sparking a lifelong passion that leads to careers in science, technology, engineering, and mathematics. This isn't merely anecdotal. Major scientific organizations and funding agencies have long recognized the power of popular culture to drive public engagement. The surge of interest following a major science fiction blockbuster can translate into increased public support for funding real-world missions, like the Laser Interferometer Gravitational Wave Observatory or the Event Horizon Telescope project, which brought us the first actual image of a black hole's shadow. These stories create a cultural appetite for discovery, reminding the public that the universe's greatest mysteries are not just for scientists in ivory towers, but are part of our shared human adventure. However, this relationship between science and fiction is not without its creative tensions. Filmmakers must often walk a fine line between factual accuracy and narrative necessity. For instance, while Interstellar's black hole was rigorously modeled, the filmmakers chose to place a habitable planet perilously close to its event horizon to serve the story, a decision that required some dramatic compression of the incredible tidal forces that would actually be present. Other films, like Event Horizon or The Black Hole, prioritize horror and adventure over scientific fidelity, using black holes as metaphorical gateways to hell rather than natural astrophysical phenomena. These more fantastical portrayals still serve a purpose, though. They use the gravitational labyrinth as a powerful metaphor for the unknown, exploring human fear, curiosity, and the ethical dilemmas of exploration. Even when the science is softened, the core concept that there are places in the universe where the normal rules break down resonates deeply with audiences and keeps these cosmic mysteries at the forefront of our cultural conversation. This ongoing dialogue between the rigorously accurate and the creatively inspired ensures that gravitational labyrinths remain a vibrant and evolving part of our storytelling landscape, continuously inspiring us to look beyond the known and imagine what might be possible. And perhaps the most powerful tool in this educational arsenal is the humble metaphor. We've used them throughout this journey: the rubber sheet for spacetime, the lighthouse for a pulsar, the echo in a cave for delayed light. These are not mere simplifications, they are essential cognitive bridges. When an educator compares the warping of spacetime around a black hole to the way a bowling ball stretches a trampoline, they are building a mental model. This model isn't perfectly accurate, but it provides a sturdy scaffold upon which a more nuanced understanding can later be built. It transforms an intimidating, abstract mathematical concept into something tangible and visual, allowing a middle school student to grasp the fundamental principle that mass tells spacetime how to curve. This process of demystification is crucial. because it breaks down the barrier that often exists between complex scientific discovery and public appreciation, making it clear that these are not magical impossibilities, but the natural, if astonishing, consequences of physical law. Several pioneering projects have dedicated themselves to this exact mission of building bridges. The Black Hole CAM project, a European research initiative, isn't just about capturing images of black holes. It has a strong public outreach component, creating animations and explanatory materials that translate their cutting-edge research into digestible content. Similarly, NAS, a universe of learning program, provides a treasure trove of resources, from professionally developed toolkits for libraries and museums to stunning visualizations and podcasts, all designed to bring the wonders of astrophysics directly to the public. These institutions understand that their work is funded by taxpayers and exists within a broader societal context. By actively engaging in outreach, they are not just sharing cool facts, they are fostering a sense of shared ownership and excitement about the cosmic discoveries being made in humanity's name. This investment in public understanding is about more than just generating goodwill. It's an investment in our collective future, a public that is captivated by the image of a black hole's shadow, that understands the significance of a gravitational wave detection, is a public that values fundamental research. This translates into support for funding scientific agencies, encourages young people to pursue STEM careers, and cultivates a culture that celebrates curiosity and critical thinking. When a child looks at a visualization of light bending around a simulated black hole and their eyes light up with a sense of wonder, that's a potential future physicist, engineer, or informed citizen in the making. That moment of inspiration, sparked by an effective educational tool, is the seed from which the next generation of cosmic explorers will grow. Ultimately, this educational endeavor brings our journey full circle. We began by marveling at the sheer intellectual achievement of understanding gravitational labyrinths, a feat accomplished by a relatively small number of brilliant theorists and observers. But through the dedicated work of educators, visualizers, and science communicators, these incredible ideas are no longer locked away in academic papers. They are brought out into the light, shared on planetarium domes, explored in interactive simulations, and discussed in online forums. This process democratizes cosmic wonder, making it clear that the universe and its mysteries belong to everyone. It ensures that the story of trapped light and warped spacetime is not just a technical footnote in the history of science, but a vibrant and ongoing part of our shared human narrative, inviting us all to be participants in the great adventure of discovery. Right now, across the globe and in the space above it, a new generation of eyes is turning toward the cosmos, armed with technology that would have seemed like pure magic just a generation ago. This isn't a quiet period of reflection in astrophysics. It's a golden age of active, aggressive discovery, a global collaboration aimed directly at probing the deepest gravitational labyrinths nature has to offer. The tools for this exploration are as varied as they are powerful, each designed to detect a different whisper from the universe's most enigmatic regions. Leading the charge is the now famous Event Horizon Telescope, or EHT, but its work is far from finished. That first historic image of the black hole in Galaxy M87 was merely the opening chapter. The collaboration is continually adding new radio telescopes to its global network, from the high deserts of Chile to the frigid plateaus of Greenland. This expanding array increases the resolution of their virtual Earth-sized telescope, allowing them to not just take a single snapshot, but to create a detailed movie of how the superheated plasma in the accretion disk moves and evolves over time. They're also turning their unparalleled gaze toward Sagittarius, a star the supermassive black hole at the heart of our own Milky Way galaxy. Studying this closer but more quiescent object presents a different set of challenges, as its appearance changes rapidly, like trying to get a clear photograph of a toddler that won't sit still. By comparing these two different black hole environments, scientists can begin to understand the fundamental dynamics that govern all gravitational traps, building a comparative anatomy of spacetime's most extreme objects. Orbiting 1,000,000 miles from Earth, the James Webb Space Telescope is conducting a different kind of investigation. While it cannot resolve the event horizon of a black hole, its incredible infrared sensitivity is perfectly suited for studying the most ancient and distant gravitational lenses in the universe. By peering back to the era of the first galaxies, JWST can detect how their light has been stretched and warped by the vast, invisible webs of dark matter that lie between them and us. Each distorted galaxy, each faint Einstein ring, is a data point in a massive cosmic survey, allowing astronomers to map the distribution of this mysterious matter with unprecedented precision. This helps us understand the largest and most subtle gravitational labyrinths of all, the dark matter halos that form the hidden skeleton of the cosmos. Furthermore, Webb is examining the environments around distant quasars, the blazingly bright active galactic nuclei powered by supermassive black holes. By analyzing the light from the gas and dust swirling around these monsters, the telescope can determine their masses and growth rates, providing crucial clues about how these ultimate labyrinths formed and evolved over cosmic time, essentially tracing their life story from the dawn of the universe to the present day. On the ground, the next great survey of the sky is about to begin with the Vera C. Rubin Observatory in Chile. This facility represents a paradigm shift in astronomy, moving from targeted observations to a relentless, comprehensive scan of the entire southern sky every few nights. Its primary mission is the Legacy Survey of Space and Time, or LSST, which will compile the largest astronomical movie ever made over the course of a decade. For the study of gravitational labyrinths, this is a game changer. The observatory's immense 3.2 gigapixel camera will detect billions of galaxies, and its repeated observations will allow it to spot the incredibly subtle distortions caused by weak gravitational lensing, the slight shearing of galaxy shapes by intervening dark matter. This will produce the most detailed map yet of the cosmic web, the large-scale gravitational labyrinth that defines the universe's structure. But it will also catch transient events in real time, like the sudden brightening of a distant star when its light is magnified by a passing foreground object in a microlensing event, potentially revealing otherwise invisible black holes or rogue planets drifting between the stars. The listening posts of the universe are also expanding their capabilities. The Laser Interferometer Gravitational Wave Observatory, LIGO, along with its European counterpart Virgo and Japan's KAGR Ray, continue to upgrade their sensitivity. With each improvement, they detect more and more mergers of black holes and neutron stars, moving from rare, singular events to building a robust catalog of cosmic collisions. This statistical approach allows scientists to answer new questions about the population of these objects in the universe. How often do they merge? What is the typical range of their masses and spins? But the future of gravitational wave astronomy lies in space. The Laser Interferometer Space Antenna, or LISA, is a planned European Space Agency mission that will consist of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart. By measuring the distance between them with laser precision, LISA will detect gravitational waves at much lower frequencies than ground-based detectors can. This will open up a whole new window onto the universe, allowing us to hear the mergers of the supermassive black holes that lurk at the centers of galaxies, a deep, rumbling chorus that would have been inaudible before. It might even detect the faint, persistent hum of gravitational waves from other exotic sources, like vibrating cosmic strings if they exist, or the extreme warping of spacetime around a stable wormhole. What makes this current era so exhilarating is the profoundly collaborative spirit that drives it. These are not isolated projects run by single nations. They are monumental international partnerships. The Event Horizon Telescope collaboration includes institutes from over 20 countries. The James Webb Space Telescope is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. The Vera C. Rubin Observatory involves a consortium of universities and research labs from around the world. This global brain trust pooling resources, intellect, and data is what makes these ambitious missions possible. It's a powerful reminder that the desire to understand the universe's deepest secrets is a universal human trait, one that transcends borders and unites us in a common, awe-inspiring goal. With every new observation, every new data point from these incredible machines, we are testing our theories against the harsh judge of reality, ready for the next discovery that will either beautifully confirm our predictions or, even more excitingly, force us to completely rethink everything we thought we knew. Yet for all the breathtaking progress we've made in mapping these cosmic mazes, we must now confront the humbling reality that some of the most fundamental questions about gravitational labyrinths remain stubbornly unanswered. These are not mere details to be tidied up by future research. They are profound theoretical challenges that strike at the very core of our understanding of physics, revealing the frontiers where our current knowledge simply breaks down. Perhaps the most notorious of these is the singularity problem, the terrifying point of infinite density predicted at the heart of a black hole by general relativity. Our equations tell us that matter is crushed to a point where spacetime curvature becomes infinite, but this is a mathematical warning sign, not a physical description. It screams that Einstein's beautiful theory, for all its power, is incomplete. It cannot handle the quantum world, and at the singularity, quantum effects must dominate. We are left with a glaring question: what truly happens at the center of a black hole? Is it a gateway to another universe, a knot of vibrating strings as proposed by some theories, or something so utterly alien we lack the language to describe it? This isn't just an academic puzzle. It represents the greatest unsolved problem in theoretical physics, the quest to unify general relativity with quantum mechanics into a single, coherent theory of quantum gravity. This challenge extends directly to the stability of hypothetical structures like wormholes. The mathematics of general relativity allows for the possibility of traversable wormholes, but as we've seen, they demand exotic matter with negative energy to prop their throats open against collapse. The central open question here is whether such matter can exist in the stable, macroscopic quantities required, or if quantum physics inherently forbids it through some yet unknown principle. Competing theories offer different answers. String theory suggests certain quantum configurations might permit it, while other approaches remain deeply skeptical. Even if we could somehow acquire it, new problems emerge. Would the intense energy densities at the wormhole's throat trigger a runaway quantum effect that destroys it? Could the very act of sending a single photon through it destabilize the entire structure? These are not just engineering hurdles, they are deep questions about the consistency of the laws of physics themselves. The debate is fierce and ongoing, a testament to the fact that on the frontier of knowledge, certainty is a rare commodity, and the most exciting ideas are often those we cannot yet prove or disprove. This engagement with the unknown is not a weakness of science, it is its greatest strength. The process of inquiry, of posing a question, wrestling with the implications, and building models to test, is what drives discovery forward. It invites us to marvel at the mystery, so let me pose a few of these open questions to you directly. Could the light trapped in a photon sphere ever be harnessed? Imagine a distant civilization somehow building a structure to capture that endless, orbiting energy. What would that look like, and what could it power? The sheer scale makes it seem impossible, but pondering it pushes our imagination about energy and technology in an extreme universe. And what would it truly mean if we one day found incontrovertible evidence of a natural, stable wormhole? It would be more than just a cosmic shortcut. It would be a revelation that our universe is fundamentally connected in ways we never dreamed, that the topology of spacetime allows for bridges instead of just barriers. It could force a rewrite of cosmology, challenge our understanding of causality, and forever change our place in the cosmos. By openly acknowledging these gaps and uncertainties, we do more than just list what we don't know. We chart the map for future exploration. Every one of these open questions is a beacon, guiding the next generation of physicists toward the breakthroughs that will inevitably come. The solutions to these puzzles won't just fill in blanks in our textbooks. They will likely revolutionize technology, redefine our cosmic perspective, and reveal a universe far stranger and more wonderful than we can currently conceive. This is the thrilling, unfinished nature of science, a reminder that the greatest adventures in understanding lie not in what we have already discovered, but in the mysteries that still await us just beyond the edge of our current light. What makes the exploration of gravitational labyrinths so uniquely compelling is that it refuses to be confined to the dusty halls of any single academic department. This isn't just a niche topic for astrophysicists. It's a vibrant, living puzzle that demands a chorus of different voices and disciplines to even begin to unravel. At its absolute foundation, this is a story written in the language of mathematics, specifically in the elegant and complex field of differential geometry. You simply cannot describe the curvature of spacetime around a black hole without the mathematical toolkit developed by giants like Bernhard Riemann and Carl Friedrich Gauss. Their work on curved surfaces, once considered a purely abstract branch of mathematics, turned out to be the precise language Einstein needed to express his theory of general relativity. Those terrifyingly complex tensors and metrics that define a gravitational labyrinth are not just physics. They are profound expressions of pure mathematics, a stunning example of how human curiosity about abstract patterns can, decades or even centuries later, provide the key to understanding the fundamental workings of the cosmos. This mathematical complexity is precisely what has driven an incredibly fruitful partnership with computer science. The equations describing the merger of two black holes are so nonlinear and intricate that they cannot be solved with a pen and paper. They require the raw number crunching power of supercomputers. This gave birth to the entire field of numerical relativity, where computer scientists and physicists work hand in hand to write sophisticated algorithms that can simulate the warping of spacetime itself. These collaborations are pushing the boundaries of what computing can do, leading to advances in processor technology, data visualization, and even the development of new programming languages optimized for handling immense datasets. And now we're seeing the next evolution, the incorporation of artificial intelligence and machine learning. Researchers are training AI systems to sift through the mountains of data from telescopes like the Event Horizon Telescope or the gravitational wave signals from LIGO, teaching them to recognize subtle patterns and signatures that might be missed by the human eye. These AIs can even suggest new solutions to Einstein's field equations, potentially uncovering new types of gravitational labyrinths that theorists hadn't even dreamed of yet. Perhaps most beautifully, this scientific journey has spilled over into the realms of philosophy and art, creating a dialogue that enriches our entire culture. Philosophers grapple with the implications of these discoveries, asking what closed time-like curves mean for our understanding of free will and causality, or how the holographic principle might reshape our conception of reality itself. Artists, in turn, have become essential partners in the process of discovery. The now iconic imagery of the black hole M87 was not a raw photograph. It was a visualization painstakingly crafted from data, a process that required artists and graphic designers to work alongside scientists to translate numbers into an image the human brain could comprehend and connect with. Exhibits in planetariums and art galleries around the world now feature stunning visualizations and sculptures inspired by gravitational lensing and warped spacetime, created by artists who are deeply engaged with the science. These works do more than just illustrate. They evoke the awe and wonder of these concepts in a way that a graph or equation sometimes cannot, making the emotional weight of the science accessible to everyone. This holistic, interdisciplinary endeavor powerfully demonstrates that understanding the universe is not a solitary pursuit, but the ultimate collective human effort. It requires the abstract rigor of the mathematician, the creative problem-solving of the computer scientist, the deep questioning of the philosopher, and the evocative power of the artist. A theoretical physicist might develop a new metric for a wormhole, but it takes an engineer to understand the materials needed to simulate it, and a graphic artist to help us all see it in our minds. This convergence of fields makes the topic of gravitational labyrinth uniquely relatable. Whether you're a programmer fascinated by big data, a student of philosophy pondering the nature of time, or someone who simply appreciates breathtaking visual art, there is a point of entry for you into this conversation. It reminds us that the drive to explore and understand is a fundamental part of the human experience, one that connects us all across artificial academic boundaries and brings us together to marvel at the impossible wonders hidden within the fabric of reality. But to truly cross the threshold from observer to explorer, we would need to move beyond just looking and listening. We would need to develop the capability to send probes directly into these extreme environments. This is perhaps the ultimate engineering challenge, requiring propulsion systems that defy our current imagination. Concepts like fusion rockets or matter-antimatter annihilation drives could provide the incredible energy needed to reach relativistic speeds, shortening the travel time to distant black holes from millennia to centuries or even decades. Once there, a probe would face an even greater hurdle, surviving the tidal forces and radiation of the accretion disk. Its design would likely need to be a marvel of nanotechnology, perhaps a swarm of microscopic, self-repairing sensors rather than a single, fragile craft, dispersing into the turbulent plasma to collect data from multiple points simultaneously. The probe's clock would tick infinitely slower from our perspective as it approached the event horizon, its final transmission stretched into a faint, fading whisper of data that could take centuries to reach Earth, a final message from the edge of oblivion. Among the most visionary of these far future concepts is the black hole bomb, a theoretical megastructure first proposed by physicist Roger Penrose and later expanded upon by others. The idea hinges on the ergosphere of a rotating Kerr black hole, that region where spacetime itself is dragged around at incredible speeds. Penrose showed that it's possible to steal energy from a black hole's rotation by firing a projectile into the ergosphere and splitting it, with one piece falling in and the other escaping with more energy than the original. The black hole bomb concept takes this a step further. Imagine surrounding a black hole with an enormous reflective shell. Light or gravitational waves bouncing between the shell and the ergosphere would be amplified with each pass through this energy-rich region, building up an exponential feedback loop of power that could, in theory, be harvested. This would transform a gravitational labyrinth from a cosmic curiosity into the most powerful energy source in the universe, a power plant for a civilization with capabilities we can barely dream of. The scale of such endeavors is so vast it invites speculation about technologies that sound like pure magic. The late, great Freeman Dyson, a thinker renowned for his boundless imagination grounded in real physics, envisioned civilizations so advanced they could dismantle planets to construct energy-capturing megastructures, the famous Dyson spheres. Applying that same visionary engineering to a gravitational labyrinth, one could imagine a Dyson novel network, a constellation of energy collectors stationed around a black hole, harnessing not just its Hawking radiation, but also the intense light from its accretion disk and the rotational energy extracted via Penrose processes. This would not be a single structure but an entire engineered ecosystem, a humming, coordinated dance of machinery operating in the most hostile environment imaginable, all feeding power to a civilization that has mastered its local region of spacetime. Yet for all this breathtaking speculation, we must constantly ground ourselves in the immense, and perhaps insurmountable, engineering challenges. The energy requirements for even the simplest interstellar probe are staggering, likely demanding a global commitment of resources spanning generations. The material science needed to build a structure that could withstand the tidal forces near a black hole doesn't exist. We would need to invent entirely new classes of metamaterials or active force fields. And perhaps the greatest challenge is time itself. These would be projects whose timelines dwarf human civilization, missions where the scientists who launch the probe know they will never see its results, and whose ultimate success would be a message for their descendants centuries hence. This forces a profound shift in perspective, from thinking in terms of quarterly reports or even presidential terms, to planning on a truly cosmic timescale, a testament to long-term thinking and patience. This forward-looking exercise is far more than just science fiction. It is a crucial function of a healthy, curious society. By daring to imagine these possibilities, we stretch the boundaries of our current science and technology. The process of theorizing about a black hole bomb forces us to ask deeper questions about energy extraction and quantum field theory in curved spacetime. Dreaming of a probe to Sagittarius, a star, pushes our engineers to develop more robust communication systems and radiation-hardened components, technologies with immediate spin-off benefits for satellites and medicine. This is how humanity progresses. By aiming for the stars, we develop the tools that improve life on Earth. It ensures that we continue to ask the biggest questions, keeping our collective imagination alive and driving the endless human quest for knowledge, preparing us not just for the eventualities of exploration, but for a future where the impossible gradually, miraculously, becomes possible. While the discovery of a natural wormhole or a stable cosmic string remains a thrilling possibility, the scientific community understands that such a paradigm-shifting event would be more than just a headline. It would be a global event requiring meticulous preparation and profound responsibility. This isn't about drafting press releases. It's about building a robust framework of verification, ethics, and international cooperation long before the first anomalous data point ever appears on a screen. The process begins with verification, a multi-layered defense against error and excitement. Imagine an observatory detecting a signature that perfectly matches a theoretical wormhole's gravitational lensing effect. The first rule is immediate and strict internal review, checking for instrumental glitches, data processing artifacts, or more mundane astronomical explanations. Following this, the finding would be subjected to the crucible of peer review, shared secretly with other independent teams around the world who would attempt to replicate the observation using different telescopes and different methods. This process, often slow and painstaking, is designed to weed out false positives and ensure that any announcement is backed by ironclad, reproducible evidence. It's a system built on healthy skepticism, ensuring that a claim of this magnitude can withstand the most intense scrutiny the global scientific community can muster. The moment such a discovery is confirmed, a separate set of protocols concerning communication and ethics would spring into action. There are existing, though non-binding, frameworks for the potential discovery of extraterrestrial intelligence, like those established by the SETI Post-Detection Task Group, which offer a starting point for discussion. For a gravitational phenomenon, similar guidelines would likely be activated, focusing on transparent, measured, and coordinated public disclosure to avoid sensationalism and public panic. Scientific bodies like the International Astronomical Union would probably take a leading role, acting as a central clearinghouse for validated information. Beyond the public, there are deeper ethical considerations. If a structure like a wormhole were found to be traversable, who would have the right to use it? Would it be considered a common heritage of humanity, like the Moon or Mars under the Outer Space Treaty, or could it be claimed by a single nation or corporation? These questions force us to confront the legal and philosophical frameworks that currently govern space exploration, which were written for a simpler cosmos and would need urgent updating to address the reality of a connected universe. This is where existing international space law becomes critically relevant. The foundational Outer Space Treaty of 1967, ratified by over 100 countries including all major spacefaring nations, establishes that space is free for exploration and use by all states, but it cannot be subject to national appropriation by claim of sovereignty. This principle would directly apply to any discovered gravitational labyrinth. No country could plant a flag on a wormhole and claim it as its own territory. However, the treaty is largely silent on the specific use and management of such a phenomenon. The subsequent Liability Convention and Registration Convention would cover damages caused by human-made objects sent to study it, but they don't provide a roadmap for stewardship of the anomaly itself. This legal gap highlights a pressing need for the international community to begin proactive discussions, perhaps through the United Nations Committee on the Peaceful Uses of Outer Space, to draft new agreements specifically for the encounter and potential utilization of exotic spacetime structures, ensuring that any exploration is conducted peacefully and for the benefit of all humankind. The practical planning also extends to the safety of any potential investigative missions. Sending a probe toward an unknown gravitational structure would be an endeavor fraught with unknown risks. Mission protocols would need to be designed with extreme caution, perhaps involving a series of increasingly close robotic scouts to map the gravitational gradients and radiation environment before any valuable spacecraft is committed. Contingency plans for a probe being lost or, in a worst-case scenario, triggering some unforeseen reaction in the structure itself, would have to be thoroughly debated and established. This isn't mere paranoia, it's a necessary exercise in responsibility. The history of science is littered with discoveries that had unintended consequences, and when dealing with the fundamental fabric of reality, the precautionary principle must be paramount. This layered approach, from data verification to legal frameworks to mission safety, demonstrates that scientists and policymakers are not just idle dreamers. They are actively engaging in the complex, practical work of preparing for a future that may one day arrive, ensuring that when and if we finally stumble upon a gateway to an impossible world, we are ready to step through it not as conquerors, but as thoughtful and humble explorers. But beyond the equations, the telescopes, and the theoretical debates, there's a deeply human question that awaits us. Why does any of this truly matter in our daily lives? Why should the average person care about the path of a photon near a singularity or the hypothetical stability of a wormhole? The answer lies not in practical application, but in perspective. Contemplating these gravitational labyrinths is a profound exercise in cosmic humility. It forces us to recognize that our everyday experience, governed by a gentle, predictable gravity, is a complete anomaly. We live in a tiny, quiet bubble of mild spacetime curvature, a protected pocket of the universe that allows life to flourish. But out there, reality is dominated by these extreme, chaotic, and beautiful structures that operate on rules far beyond our intuitive grasp. Understanding this doesn't just teach us physics, it recalibrates our sense of place. We are not the center of the universe, we are fleeting observers on a small rock, lucky enough to have evolved the consciousness to even begin to decode the magnificent, violent ballet happening all around us. This journey into the impossible also speaks to a fundamental human drive that has defined our species since we first looked up at the stars, an insatiable curiosity. It is the same urge that drove ancient navigators to map the oceans and early astronomers to chart the planets. We are compelled to explore, to understand, to push at the boundaries of the known. Gravitational labyrinths represent the ultimate frontier of that curiosity. They are puzzles written into the fabric of reality itself, and the simple, thrilling fact that we can use mathematics and technology to unravel them is a testament to the power of the human mind. There's a pure, childlike wonder in realizing that a concept dreamed up by a patent clerk in Berlin over a century ago can accurately predict the shadow of a black hole we photographed 65 million light-years away. That connection between human thought and cosmic truth is a profound source of meaning and inspiration. Many of the scientists who dedicate their lives to this field describe moments of breathtaking awe that are as emotional as they are intellectual. Astrophysicist Janna Levin often speaks of the experience of hearing the first gravitational wave signal, GW 150,914, not just as a data point, but as a piece of cosmic art, a direct message from the universe that we had finally learned to listen in a new way. She describes the chirp as a poem, a beautiful and stark confirmation of Einstein's vision. Similarly, the late Stephen Hawking, despite his physical limitations, frequently talked about the joy and freedom of being able to mentally roam across the cosmos, to travel through space and time in his mind to explore these incredible phenomena. For them, and for so many others, this work is not a dry, academic exercise. It is a deeply personal and moving dialogue with the universe. This personal connection is what transforms abstract science from a niche interest into a shared human endeavor. When we marvel at an image of a black hole's shadow, we are participating in that same wonder. We are joining a chain of curiosity that stretches back generations and will hopefully extend far into the future. By engaging with these ideas, we are not just passive consumers of information. We are actively supporting a culture that values asking big questions, that invests in fundamental research for the sake of understanding alone. This cultural support is what builds telescopes, funds research grants, and inspires the next generation of scientists. The story of trapped light is ultimately our story, a narrative about a curious species on a pale blue dot, slowly and patiently figuring out its place in an astonishingly vast and mysterious cosmos, finding beauty and meaning in the most impossible of places. One of the most persistent and dramatic myths about black holes is that they act like cosmic vacuum cleaners, relentlessly sucking in everything around them. This image of an all-consuming monster lurking in space makes for great science fiction, but it's a serious oversimplification of how gravity actually works. A black hole's gravity is no different in nature than the gravity of a star or a planet. It simply operates in an environment of unimaginable density. If you were to magically replace our Sun with a black hole of exactly the same mass, Earth and all the other planets would continue to orbit it perfectly normally. They wouldn't be instantly pulled in. The key difference is the proximity required to be in peril. With a star, you can get relatively close before its gravity becomes overwhelming. But a black hole's immense mass is concentrated into a point of near zero volume, meaning you can get much closer to the source of that gravity. The danger zone isn't everywhere. It begins only when you cross the event horizon, the point of no return. Outside of that boundary, objects can still maintain stable orbits, just as planets orbit a star. The accretion disks of superheated gas we see are not a sign of a vacuum pulling material in from light years away. They are the result of material that was already on a trajectory to fall close to the black hole, much like how comets fall toward our Sun. The black hole itself doesn't suck. It simply has a gravitational influence so intense that within a certain distance, not even light can escape its grip. Another popular misconception, heavily fueled by movies and television, is the idea that wormholes are stable, easily navigable tunnels just waiting for a spaceship to fly through. The reality, according to our current understanding of physics, is far more complex and restrictive. As we've discussed, the equations of general relativity do allow for the theoretical possibility of wormholes, often called Einstein-Rosen bridges. However, the vast majority of these mathematical solutions describe structures that are completely impractical for travel. They are often incredibly unstable, predicted to collapse into a singularity the instant they form, potentially before even a single photon could pass through. The only proposed way to prevent this instantaneous collapse is with a hypothetical substance known as exotic matter, which possesses negative energy density and negative pressure to prop the wormhole's throat open. But this isn't something we can just mine from an asteroid. The existence of stable, macroscopic exotic matter is purely speculative, and the quantities needed to stabilize a wormhole large enough for a person are astronomical, far beyond anything conceivable with known physics. Furthermore, even if such a structure could be created, the radiation and tidal forces inside would likely be lethal, stretching any object into a stream of atoms, a process known as spaghettification. So while wormholes are a fascinating theoretical tool for exploring the implications of general relativity, they are a far cry from the convenient interstellar subway system often depicted in pop culture. A third common misunderstanding revolves around the nature of light itself within these gravitational traps. There's a notion that light simply gets stuck or stops in a photon sphere, like a car running out of gas. This isn't accurate. Light, by its very nature, always moves at the speed of light through spacetime. What's happening in a photon sphere is far more interesting. The spacetime around the black hole is so severely curved that the path light would normally take in a straight line is bent into a perfect closed circle. The photon isn't slowing down or stopping. It is following a circular orbit, perpetually falling toward the black hole, but moving sideways so fast that it keeps missing it. It's akin to a satellite in a perfect circular orbit around Earth, constantly falling toward the planet, but with a forward velocity that ensures it never gets any closer. This orbit is also profoundly unstable. The slightest perturbation, an interaction with a stray dust particle, or the gravitational influence of a nearby star, would be enough to knock the photon out of its delicate balance, sending it either spiraling down across the event horizon or flying out into the wider universe. This clarifies that trapped light isn't motionless or captured in a static sense. It is caught in an incredibly precise, high-speed celestial dance dictated by the warped geometry of space. Finally, it's crucial to address the myth that these concepts are purely theoretical with no basis in observational science. While wormholes and exotic matter remain in the realm of hypothesis, the foundational principles are tested and verified. We have direct visual evidence of black holes from the Event Horizon Telescope, which captured the shadow of M87's singularity surrounded by the glowing accretion disk, its light bent by the intense gravity. We have measured the gravitational waves from merging black holes, vibrations in spacetime that perfectly match the predictions of general relativity. Gravitational lensing, where the light from distant galaxies is warped by intervening mass, is a routine tool used by astronomers to map the universe. These aren't just abstract ideas, they are observed phenomena that confirm the extreme effects of gravity as described by Einstein. By dispelling these myths, we don't diminish the wonder of gravitational labyrinths, we enhance it. The truth is far more fascinating than fiction. A universe where spacetime can be curved into knots, where light can be forced into orbital loops, and where our understanding of reality is constantly being challenged and refined by the incredible cosmos we inhabit. Now I want to turn the tables and hear from you, because the most fascinating ideas often come from outside the lab. Imagine for a moment that you're the cosmic architect, with the power to design your own gravitational labyrinth from scratch. What would it look like? Would you create a serene, beautiful maze of gently curving light, like an eternal, slow-motion aurora dancing around a central point of darkness? Or would you engineer something far more practical, a stable, traversable wormhole with a clearly marked entrance and exit, a celestial superhighway for future explorers? Perhaps your design would be purely artistic, a temporary sculpture of warped space-time meant to be observed and admired before it peacefully dissipates. The beauty of this thought experiment is that it pushes us beyond the known laws of physics and into the realm of pure imagination, where the only limit is our creativity. Let's bring that concept down to a more tangible level. How do you believe the actual discovery of permanently trapped light, a confirmed, observable photon sphere around a distant black hole, or something even more exotic, could fundamentally alter our technology here on Earth? While we might not be able to harness that light directly, the principles we learn from studying it could lead to revolutions in fields we can barely foresee. Could it inspire new forms of energy generation that tap into the fundamental geometry of space itself? Might it lead to breakthroughs in material science, giving us substances that can manipulate light in ways that seem like magic to us now, perhaps for perfect cloaking or light-based computing? Or could the very concept of trapping information in light, much like it's trapped in a photon sphere, lead to entirely new paradigms in how we store and transmit data across vast distances? The history of science is filled with examples of pure research leading to unexpected and world-changing applications, from quantum mechanics giving us the transistor to the mathematics of relativity making GPS possible. This is where you come in. I am genuinely fascinated to read your ideas in the comments below. What kind of impossible world would you want to explore first if you had a spacecraft capable of surviving the journey? Do you think the ultimate purpose of understanding these gravitational labyrinths is to one day travel through them? Or is their true value the way they deepen our fundamental understanding of the universe's blueprint? Your perspectives are incredibly valuable. This channel thrives on our shared curiosity, and your comments often introduce angles I hadn't considered, helping to shape the topics we explore together in future videos. This isn't just a one-way conversation. It's a community dialogue where every voice adds to our collective understanding. So please share your thoughts, your wildest theories, and your most pressing questions. Let's continue this adventure together, unraveling the mysteries of the cosmos one idea at a time. Throughout our journey into gravitational labyrinths, we've navigated a landscape built upon a few profound and interconnected principles that shape our entire universe. At the very heart of it all lies Einstein's revolutionary insight that gravity is not a mysterious force acting at a distance, but rather the curvature of spacetime itself caused by the presence of mass and energy. This single idea that massive objects warp the very fabric of reality is the foundational bedrock for everything we've explored. It explains why light, which always follows the straightest possible path through this curved spacetime, bends around stars, gets lensed by galaxies, and can even be forced into orbital loops around the most extreme objects. Without this geometric understanding of gravity, the very concept of a gravitational labyrinth simply wouldn't exist. Light would travel in perfect straight lines forever, never being captured or twisted into impossible knots. This warping of spacetime directly leads us to the critical role of mass and density in creating these cosmic traps. It's not just mass alone, but how concentrated that mass is. A star like our Sun has immense mass, but it's spread out over a large volume, creating a gentle gravitational well. However, crush that same mass into an impossibly small space like a city-sized neutron star or a point like singularity, and the spacetime curvature at its surface becomes so extreme that the rules of physics as we know them begin to break down. This incredible density is what creates the steepest gravitational wells, the ones with sides so sheer that not even light has the escape velocity to get out. The event horizon of a black hole marks the point of no return for this very reason. The spacetime curvature is so intense that all possible paths for light and matter lead inexorably inward, a one-way street into the ultimate unknown. From this, we arrive at the fascinating phenomena that define the labyrinths themselves, with the photon sphere serving as a perfect example. This isn't a solid shell, but a precise region where the curvature of spacetime is so specific and so severe that it forces light into a perfect circular orbit. It represents a delicate, unstable balance between the photon's innate motion and the black hole's relentless pull. This concept beautifully illustrates how gravitational traps aren't always about complete capture. They can be dynamic regions of complex interaction. The photon sphere acts as a boundary, a last stable orbit that separates paths that might still escape from those destined for the void. It shows us that these labyrinths have intricate structure and geography, with different zones governed by different sets of rules for how light and matter can behave. These core principles don't operate in isolation. They weave together to form the complex tapestry of a gravitational labyrinth. Spacetime curvature, dictated by mass and density, creates the potential for traps. The photon sphere demonstrates a specific, precise manifestation of that trapping potential. And when we add rotation, as described by the Kerr metric for spinning black holes, the complexity multiplies. The dragging of spacetime around a rotating object creates an ergosphere where nothing can remain stationary and introduces the possibility of even more complex orbits and energy extraction. This interplay shows us that these are not static prisons but dynamic, energetic environments where gravity, motion, and light engage in a cosmic dance with profound implications for the energy output of quasars and the very evolution of galaxies. Furthermore, this framework extends beyond the incredibly dense to the incredibly diffuse. The same principle that creates a sharp photon sphere around a black hole also operates on a galactic scale within the vast, invisible halos of dark matter. Their immense collective mass gently bends the light from billions of background galaxies, creating a statistical labyrinth, a weak lensing effect that, while not trapping individual photons forever, nonetheless sculpts the light we see across the cosmos. This connects the most extreme, localized traps to the largest-scale structures in the universe, showing that the same physics operates across an astonishing range of scales, from the infinitesimal to the cosmic. Ultimately, these key ideas form a powerful and coherent narrative. Mass tells spacetime how to curve. That curvature tells light and matter how to move. Under the most extreme conditions of density and energy, that movement can become trapped, orbited, or bent into pathways that defy our everyday intuition. Understanding these foundational connections allows us to see the unity in the chaos, from the elegant simplicity of a photon sphere to the mind-bending possibilities of a wormhole. It provides the theoretical toolkit we need to not only appreciate the majesty of these impossible worlds, but to also interpret the observations from our telescopes and the signals from our gravitational wave detectors, bringing the abstract mathematics of relativity into stunning, tangible focus. Yet as we marvel at these intricate cosmic traps, from the delicate photon spheres to the vast dark matter halos, we must finally pull back the lens to their grandest possible scale and ask the most profound question of all: what is the ultimate cosmic significance of these gravitational labyrinths? How do these bizarre, often invisible structures not just exist within our universe, but actively shape its destiny, from the largest galaxies to the flow of time itself? The answer reveals that these are not mere cosmic curiosities. They are fundamental architects of reality, playing a silent but decisive role in the story of everything. Consider first the evolution of galaxies. At the heart of nearly every large galaxy, observations suggest, lurks a supermassive black hole, a gravitational labyrinth of unimaginable power. For decades, this was seen as a strange coincidence, but we now understand this is no accident. It is a symbiotic relationship. These central black holes act as regulatory engines for their entire host galaxies. When a galaxy consumes too much gas and grows too rapidly, the material funneling toward the central black hole ignites it into a brilliant quasar. The tremendous energy and radiation blasting from this active nucleus then blow away the surrounding gas and dust, effectively shutting off the raw material for new star formation and halting the galaxy's growth. This feedback process, governed by the physics of the accretion disk labyrinth, is why we don't see endless, runaway galaxy growth. It is a cosmic balancing act, where the most extreme gravitational trap in the universe acts as a governor, setting limits and shaping the population of stars we see across the cosmos. Without these central black holes and their intricate dynamics, the universe might look utterly different, a place of fewer, more bloated galaxies with a completely different history of stellar birth. The influence of these labyrinths extends to the most mysterious substance in the universe, dark matter. We cannot see dark matter, but we know it exists through its gravitational pull, and it is the primary scaffolding upon which all visible structures are built. Gravitational labyrinths, particularly the subtle but immense ones formed by dark matter halos, are the tools that let us map this invisible cosmos. The way they lens the light from distant galaxies provides our only means to chart the distribution of this enigmatic substance. But the connection may be even deeper. Some theories, like those involving primordial black holes or other exotic compact objects, suggest that certain types of gravitational labyrinths might actually be the dark matter. Or perhaps the properties of dark matter are intimately tied to the formation of these traps in the early universe. By studying the most extreme warps in spacetime, we are indirectly probing the nature of the invisible stuff that makes up 85% of all matter, a quest that gets to the very heart of what the universe is made of. This grand perspective inevitably draws us toward the universe's ultimate fate and its deepest mysteries, like the arrow of time. The relentless forward march of time from order to disorder is encapsulated in the concept of entropy. And there is no greater source of entropy in the universe than a black hole. The event horizon of a black hole represents a one-way door, a point of no return that forever increases the total disorder of the cosmos. Some physicists, like Sean Carroll, have even suggested that the conditions necessary for the arrow of time to emerge a low-entropy past might be intimately connected to the gravitational collapse that forms these labyrinths in the first place. Furthermore, the theoretical existence of closed time-like curves within certain wormhole solutions presents a direct challenge to our understanding of causality and time's flow. While these may not be physically possible, their very existence in our equations forces us to ask why time has a direction at all, and whether gravitational labyrinths hold a clue to this most fundamental property of our experience. This journey of understanding connects to the most expansive ideas in all of cosmology, including the multiverse. In some string theory models, our universe is a four-dimensional membrane floating in a higher dimensional bulk. In this view, a black hole in our universe might be intimately connected to a gravitational labyrinth on another brane, or perhaps even be a gateway to it. The singularity at its center might not be an end, but a bridge to another universe with completely different physical laws. While firmly in the realm of speculation, this idea illustrates how the study of these extreme objects pushes our thinking to the absolute limits, forcing us to consider that our entire cosmos might be just one part of a much vaster, richer multiverse, with gravitational labyrinths serving as the potential seams or connections between different realities. This elevated view makes one thing perfectly clear: the study of trapped light and warped spacetime is far more than a technical niche within astrophysics. It is a fundamental part of the human endeavor to understand reality itself. We are using the most extreme environments the universe can provide as natural laboratories to test our ideas about space, time, matter, and energy under conditions we could never hope to recreate. Every observation of a gravitationally lensed quasar, every simulation of a colliding black hole, every delicate measurement of a photon sphere's properties is a data point in our collective effort to answer the biggest questions we can ask. Where did the universe come from? What is it made of? How will it end? And what is the nature of the physical laws that govern it all? The gravitational labyrinths are not just puzzles to be solved. They are the keys to the cosmic kingdom, holding within their twisted geometries the secrets of existence. This pursuit may never yield a faster smartphone or a more efficient engine, but it fulfills a deeper human need, the need for wonder, for perspective, and for the profound appreciation that comes from knowing we are part of a story that is far grander, stranger, and more beautiful than we could have ever imagined. If this journey through gravitational labyrinths has sparked your curiosity, the adventure is only just beginning. There are so many incredible resources waiting for you to explore, designed to take you even deeper into the wonders of general relativity and astrophysics. For a truly immersive experience, I highly picking up a copy of Kip Thorne's Black Holes and Time Warps: Einstein's Outrageous Legacy. It reads like a thrilling scientific detective story, making even the most complex concepts accessible and exciting. If you're more of a visual learner, the documentary Black Hole Apocalypse from Nova is a fantastic choice, available on PBS and various streaming platforms. It brings these cosmic mysteries to life with stunning visuals and clear explanations. And for those who prefer structured learning, platforms like Coursera and edX offer excellent introductory courses on astrophysics from top universities. many of which you can audit for free, allowing you to learn at your own pace from world-class professors. To make sure you don't miss our upcoming explorations into other space mysteries, be sure to hit that subscribe button and tap the bell for notifications. Our channel is dedicated to unraveling the cosmos's biggest puzzles, and we have deep dives planned on related topics that you won't want to miss. We'll be venturing into the enigmatic realm of dark energy, the mysterious force accelerating the universe's expansion, and probing the cutting-edge theories of quantum black holes, where the rules of the very small meet the laws of the very large. By subscribing, you're joining a community of curious minds eager to understand the universe's most profound secrets. If you found this video enlightening, please consider sharing it with a friend, a family member, or on your social media feeds. You might just ignite that same spark of wonder in someone else. For continued discussion and discovery beyond this video, I encourage you to connect with some truly amazing online communities and resources. The website Physics Forums is a wonderful place to ask questions and engage in thoughtful conversations with both enthusiasts and experts. For reliably accurate and up-to-date astronomical news, NASA website and their astronomy picture of the day are absolutely essential daily bookmarks. Platforms like Ars Technica and Sky and Telescope also offer fantastic articles that break down the latest discoveries in an engaging way. This direct engagement is about more than just building an audience. It's about fostering a greater appreciation for science and critical thinking in a world that deeply needs it. Your involvement helps create a more informed and inspired global community, proving that the quest for knowledge is a shared human endeavor that connects us all under the same vast starry sky. As we conclude our journey through the physics of gravitational labyrinths, remember that these impossible worlds are not just theoretical fantasies. They are active frontiers where our very understanding of reality is continually tested, shattered, and remade. Each concept we've explored, from the elegant, precise curves of light orbiting a black hole's photon sphere to the mind-bending speculative realms of traversable wormholes, serves as a profound challenge to expand our perspective. They compel us to think bigger, to question deeper, and to embrace the beautiful complexity of a cosmos that refuses to be easily categorized. This exploration is far more than an academic exercise. It is a testament to humanity's unyielding curiosity and our relentless drive to make sense of the magnificent universe we inhabit. The fact that we can use mathematics, developed here on our pale blue dot, to accurately predict the shadow of a monster black hole millions of light years away is nothing short of miraculous. It connects us directly to the cosmic dance, transforming us from passive observers into active participants in a grand, ongoing investigation. I truly hope this journey has ignited a spark of wonder within you, revealing that the universe is not a static backdrop, but a dynamic, explosive arena full of mysteries waiting for their moment to be uncovered. Your engagement with these ideas is what keeps the spirit of discovery alive. So thank you sincerely for dedicating your time and curiosity to join me in unraveling these deep mysteries. The adventure does not end here. Keep looking up at the starry canvas above, stay relentlessly curious in your daily life, and let's continue this incredible exploration of the cosmos together. I am genuinely eager to hear which concept captivated you the most. Was it the haunting reality of black holes, the tantalizing possibilities of wormholes, or perhaps the subtle, universe-spanning influence of dark matter? Share your thoughts and questions in the comments below. Your perspective adds a vital voice to our shared quest for understanding. And if you want to ensure you don't miss our next dive into the unknown, please like this video, subscribe to the channel, and share it with anyone else who marvels